Hi everyone, can you hear me? Okay, can you please confirm quickly if I'm audible, if everything is fine? Okay, great. So let's get started. So today we are going to see shortest path algorithms. So there are many algorithms that we want to discuss today, and interestingly, those algorithms are also very nice algorithms, which means that we will see the complete analysis of all the algorithms, right? So we will not just see that okay, this is the algorithm, this is the time complexity. We will see the complete analysis. So which means that I will tell you that that this particular algorithm is basically having why this particular algorithm is working, why this particular algorithm won't work, and these kind of things, right? So I will also tell you something called as proof. Okay, intuitive proof I will tell you, okay, that why this algorithms work, okay, why this work, be it any algorithm. I will tell you the proof of that algorithm also. So let's get started with this topic, which is shortest path algorithms. Now, the very first algorithm for the shortest path we will see is BFS, which is called breadth first search, right? BFS, breadth first search. So why we are studying this particular algorithm in the shortest path? Like, I mean, generally this particular algorithm is not discussed in the shortest path, right? So why we are discussing this in the shortest path, and how you can find the shortest path using BFS, we will see. In fact, there are a couple of gate questions also. We will also solve those gate questions, that how BFS is there to solve the shortest path problem. Okay, so let's just quickly first understand what is BFS and how it is working, right? So for example, this graph is given to you. Now if I ask you that can you draw the BFS tree of this graph, BFS tree of this graph, then can you draw this? So which means you can start with one of the vertex. Let's suppose for example I'm starting with this one. Okay, so suppose I'm starting with this one, then you go to all the neighbors of this one. So 2 is the neighbor, 5 is the neighbor, and 6 is the neighbor. So these are the three neighbors. So 2 is the neighbor, 5 is the neighbor, and 6 is the neighbor, right? These are the three neighbors: 2, 5, and 6. Now you pick one of the neighbor, which is 2, and then you go to the neighbors of 2, which means you will go to 3, right? And 5, but 5 is already visited, which means 5 is already already you have explored this 5, so you will not write 5. So I think neighbor of 2 is only 3, right, which is unvisited. Now you will pick this 5. Okay, you will pick this 5, and then you will say that okay, this 5 is basically having which unvisited neighbor, it is 4, right? So you will say that okay, this 5 is basically having 4, and then you will pick this 6. So I think this 6 doesn't have any unvisited, so I think this is done. And similarly for 3, there is no unvisited. Now there is no unvisited for 4, so this is called BFS tree, right? This is called BFS tree for this given particular graph. Okay, so I hope you understood that how to draw the BFS tree. Let me know if there is any doubt in drawing the BFS tree itself. Okay, so this is quite easy. Now suppose that I ask you that how you draw this tree using the Q, which means that we use Q in the BFS, right? So let's just see BFS using Q quickly. Okay, using Q. So by the way, this is basically the revision session. Okay, this is the revision session, which means little bit I'm expecting that you already know. Okay, little bit I'm expecting that you already know. Okay, now let's just see the BFS using Q. For example, that this is a graph which is given to you, and now suppose that I start with this particular vertex again 1. So I will push this vertex 1 in the Q, right? I will push this vertex 1 in the Q. This is a Q. This is a Q. Okay, now this particular one is pushed. Now I will do what? I will basically dequeue this. I will basically remove this one. Okay, and I will put all the neighbors of 1 here. Now this 1 is removed. Now can you tell me what are the neighbors of 1? 2, 5, and 6, right? 2, 5, and 6 are neighbors. Okay, you can put in any order, which means you can put 5 first and 2 and then 6. It doesn't matter. Okay, suppose I'm putting here 2, 5, 6. Okay, 2, 5, and 6. And what are these 2, 5, 6? These are neighbors of 1. Okay, n1 here, I mean that neighbors of 1. Have you understood? So how this algorithm is working is basically basically saying that okay, you put this one, and then you put all the neighbors of this. You pop out this one and put all the neighbors of this. Now you pop out this 2. put all the neighbors of 2. Okay, so you pop out this 2 and put all the neighbors of 2. So what are the neighbors of 2? What are the neighbors of 2? Can you tell me? The neighbors of 2 are 3, right? It's 3 only basically. I mean 5, 6 are already done, so that's why it is 3. So that's why you pop out it, which means you will write it here, and then you put all the neighbors of 2, which is 3 only, right? These are the neighbors of 2. Understood? Let me know if that is okay. Okay, till this point, let me know if that is okay. Okay, great. So basically, we are just understanding how to use BFS using the queue. Now, what you will do? Now you will say that, okay, now I will pop out this 5. Okay, and you put all the neighbors of 5. What are the neighbors of 5? I think this is 4, right? I think this is 4. So that is why you will pop out this. You will pop out this, and then you will put the neighbors of 5, which is 4, right? Okay. So this is neighbor of 5. Is this understood? Okay, great. Now what you will do? You will say that, okay, now let's just pop out this 6. Okay, if you pop out this 6, then you will write the 6 here and put all the neighbors. Since there is no other neighbor, so that's why you will write it directly. Now you pop out this 3. There is no neighbor of 3. You pop out this 4. There is no neighbor of 4. So 1, 2, 4. Sorry, 1, 2, 5, 6, 3, 4. This is one of the order that you have got, right? Okay, I mean in this order you are basically exploring this using BFS, right? So basically this is how algorithmically you will do, right? This is how algorithmically you will do. Hope you understood. Okay, now see here, this is one of the tree that we are getting, and this is called BFS tree, right? Bedford search tree. So for example, let's suppose there is a huge graph which is given to you. Can you draw the BFS tree here? Starting from, let's suppose, some vertex. Let's suppose you are starting from this one. Okay, can you draw the BFS tree? Let's just quickly draw it for the sake of practice, right? So one will explore the neighbors, which is 10 and 9, and then you pick one of this. Okay, let's suppose this is 13. Then you pick one of this. Let's suppose you are picking 10, and then you will say, okay, this is 13. Okay, this is only one neighbor. Now you pick this 9. Okay, now you pick this 9. Then you will say that this is 13 is already explored. So 12 is only remaining, right? So from this 9, 12. And then what else? Now see, 10 is done, 9 is done. So basically we are going label by label. Okay, from this tree you can understand that we are going label by label, right? So this 10 is done and 9 is done. And now you pick this 13, and then you go to the neighbors of this 13. So what are the neighbors? 0 is the neighbor, right? 0 is the only unvisited neighbor, which is done, right? Which is done. And now you pick this 12, which means in terms of queue, I will say that you are popping out this 12, right? You are popping out this 12. Okay, in the queue. See, you are popping out this 13, and then only you are exploring. You can say you are exploring its children, right, or its neighbors. So you have to pop out here. Okay, in terms of queue. Don't worry, you will get to understand more. Okay, what I'm saying here, I will tell you. I will tell you the relationship with the queue. Okay, the tree that I'm making is basically one-to-one correspondence with the queue, which means this 0 is here, no doubt, right? This 0 is here, no doubt, and then this 13, 0 is done, and then basically what you will do, now you will go to this 12. What are the neighbors of 12? You will say that, okay, let me just pop out this 12 and let me just push all the neighbors of this 12. Okay, so the neighbor is only 2, so which means this 2 now, right? Now you will pop out this 0 and put the neighbors of this 0. So which are 7 and 11. You can put in any order. Let's suppose 7, I'm putting first, and then 11. Now you pop out this 2 from the queue and then put all its neighbors. So it is you will say 3, only 3, right? Currently it is only 3. And then you will pop out this 7 and then put all the neighbors. So 3 is done. So you will say 6 is the only neighbor here, right? So here, if I just ask you the neighbor, then you will say 6 is the neighbor for the 7, and for this 3 basically 3, 11, these are done, I think, right? And now let's just see 11. So 11 neighbor is done, and now let's just see 3. What are the 3 neighbors? It is 4, right? It is 4. Now let's just pick 6, and 6 neighbor is 5. So basically this is one of the BFS tree that you will be getting, right? Let me know if that is understood to everyone. This is one of the BFS tree starting from 1, right? So basically you will keep on going to the neighbors. So here the BFS tree is saying that you will keep on going to the neighbors, and then you pick the first neighbor, then you go to the neighbor. So it is going basically neighbor by neighbor, like that, right? Easy. Do you want to try the BFS here, BFS tree? Okay, can you try the BFS tree quickly? So you can start with, let's suppose, A, and then you go to the neighbor of A, which is, let's suppose, B. Okay, so currently it is B, and then you start with B, then you will go to C, and then from this B you can also go to G. So these are the neighbors. I think I think these are the only two outgoing edges here, C and G. And then from you pick this C, there is one outgoing edge which is E, right? And then you pick this G, there is one outgoing edge only, which is, I mean, two outgoing edges, G and C and A, so which are already done, so you don't need to write it. And then you come to this E. Now can you tell me that what are the outgoing edges to this E, which means what are the neighbors to this E? So the neighbors, if I need to write the neighbors of this E, then you will say that E is here and the neighbors of E is nothing, right? So I mean, this is done. Then you will go to G. So what are the neighbors of G? Okay, sorry, G was already done, right? Yeah, this is C, and which is already done. So I think A is done, B is done, and C is done, G is done. I think F and D are not even reachable. So basically this BFS is leading to the forest, not just tree. The BFS is leading to the forest, right? This is basically leading to the forest, which means currently you have not explored all the nodes, but if you see, then you need to explore this F also. So you will go to the F separately, and then you will go to the D separately, right? So this is the BFS forest. So here we learn that VFS can also lead to the forest, just like DFS. If you have seen the DFS video, okay, then you will get to understand that DFS can also lead to the forest. So this is about the BFS, which can also lead to the forest. Okay, I hope you understood that how to run the BFS. Now, if you might have noticed one thing, that DFS tree, it tend to be long and skinny, while BFS tree are short and fat. What do I mean by that? Let's suppose there is some graph which is looking like this, right? Okay, which is, let's suppose, looking like this. Now suppose this is A, this is B, this is C, this is D, this is E, right? Now if you make the DFS tree, okay, if you make the DFS tree, generally it will go in the depth first manner, which means it will be basically tall, which means A, B, C, D, E, like this, right? It will be, generally it is tall, right? It is quite tall. But if you make BFS tree, okay, if you make BFS tree starting from A only, then it will go to B and then E, and then from this B it will go to C, and then from this E it will go to D. So it is short and fat, right? That's what they are saying. It is short and fat. So BFS tree is short generally, and DFS tree is basically long and skinny. Okay. Anyway, so this is one point that I wanted to discuss. Now let's just see this GATE 2008 question, which is very easy question. What they are saying, that BFS has been implemented using the queue data structure. Okay. One possible order of visiting the following graph is. So can you tell me that is this the correct order, which means that BFS can go to the M and then N and then O. Is this possible? M and O. Is this possible? Is A possible? M and O? No, right? Because why this is not possible? Because M, N, and then it should be Q and R, right? So this is not possible. What about N, Q? What about N, Q, and then M? N, Q, M. Yeah, so from this N you are going to Q and M, and then they are saying that P, O, R, and then P. Is this possible to go to P from this N? No, right? No. So I don't think this is possible. See, from this N you can go to Q, that is fine, and then also you can go to M, that is also fine. I mean, you will go to the neighbors, and then you will go to O only, right? Then the next should be O. Okay, N, Q, M, and the next should be O. This should not be P. Okay, this should not be P. So that's why this is not the answer, right? Okay. So what about option C? What about option C? Option C is saying Q, M, N, P, R, O. Q, you go to Q and then M and then N and then P. Okay, and then can you go to, okay, so basically this is interesting. I think this is possible. So from this Q you can go to M, then N, then M, N, and then P, right? So in this order they are going. Then you will pop out this M first, right? So you will pop out this M, then you will go to the neighbors of M. So which means you have to go to R. Okay, M and P, and then you are going to R. So yeah, that is correct, right? That is correct. M and P are, and then you can go to O. So I think that is correct. But Q, M, N, and then can you go to P? So Q, M, N, P, and then can you go to O? Q, M, N, P, and then can you go to O? This is wrong. See, after Q, M, N, P, after this Q, M, N, P, you have to go to neighbors of M only, because M is the first vertex that you will be pushing in the Q. So once this is done, then you have to go to the neighbors of M only, which means that has to be R only. And then you will say that this is done, this is done, this is done, and then this is done, and then you will go to the neighbors of N, which is basically O, right? So this is the correct order, right? Understood? So basically C is the correct answer and D is not the correct answer, right? Okay, you can just draw the tree and see that which one is the correct answer. So C is the answer here. Now let's just see one interesting thing, which is called BFS Q state or the front triggers. So let me quickly discuss this, and then we will come to the point that why BFS can be used as a shortest path algorithm. Okay, so here let me just discuss one thing, which is the front triggers. So what do I mean by that? See, let's suppose you run the BFS on A. Okay, then can you tell me what is the current Q state? Which means in the Q you must have pushed the A. Basically, now I want to tell you that how this Q and the tree are related to each other, okay? Then you must have pushed this A, sorry, you must have popped this A, and then you are saying, now let me explore the neighbors of A, right? So you pop this A and then explore, which means then push, okay? Push or the NQ, the neighbors of A, which are B and G, right? Which are B and G, okay? And now, once this is done, then you pick B and push the neighbors of B. So what are the neighbors of B? See, you are basically, now you pop out it. Now you're pushing B and G. Okay, B and G. Once this is done, you will pop out this B. Okay, you will pop out this B and push the neighbors of B, which is C only, right? So basically, if I tell you, okay, till now, if I tell you that this is the tree state, okay, this is the tree state. So you have pushed this C. This is the tree state, and I mean this is the partial BFS tree that we have made till now, right? So this is the partial BFS tree that we have made till now. And then if I ask you that what is the state of the Q, then you will say the Q is currently looking like this, right? Q is currently looking like this, which means G and C are in the Q. Is this okay? So if I tell you the partial state, okay, and then if I ask you the Q, then you observe one thing, that if the internal node is there, okay, that must have been popped down from Q. See, the internal node, whatever is the internal node, right? These are the internal node. These internal node must have been popped out. Why? Must have been popped out. Can anyone tell me why? Which means, given this, let's suppose I ask you this. Let's suppose this is some tree, okay, some partial BFS tree, okay, some partial BFS tree that I have. Now, can you tell me, this is, let's suppose A, B, C, D, E, F, okay. Now, let's suppose, I hope this is visible. Now, let's suppose if I ask you, the question is here, given is partial BFS tree, then what vertices can be in Q at this point? Okay, let's suppose this question is MSQ. Okay, this question is MSQ. So what vertices can be in the Q at this point in time? And then let's suppose they give you the option is A. Okay, A is, I mean, this is one of the option, that A, and then B, can this D, okay, can this F. So what are the answers? What are the answers here? Can you tell me? See, this is A. Can this be in the Q? See, this partial tree is given to me. Can this A be in the Q currently? No, this must have been popped out. Then only you are exploring its neighbor, right? See, you have explored this A. It means you must have been popped out it. and then you must have been popped out this B also, then you must have been popped out this C also, right? So A, B, C can never be. Can this D? Maybe. Can this F? Maybe. So D and F are the answers here, right? Right? D and F are the answers here. If E is also the option, then E would have been the answer. If E is also the option, then E would have been the answer. But currently E is, let's suppose, not the option. So I mean, there is no option to take here, right? So here, as per this question, D and F are the answers, right? So basically the leaps, that's what I'm trying to make a point, that this leaps can be the part of the tree, right? So they must have been popped out. Okay. I mean, the internal nodes must have been popped out. So this is what I mean by saying the frontiers. These are called frontiers. Frontiers means at the front. So suppose you are here and you're looking from here. Okay. Then what you will see? You will see C and G. Basically, the leaves are called frontiers. Anyway, don't worry about the terminology. Let's just understand this more. Okay. So you will say that, okay, C is there, and then yeah, B, C, okay, B, you will explore its neighbors, then B. Okay. Now you tell me at this current state, okay, at this current state, what is the next neighbor? Okay, let's suppose if I ask you, that given this, let's suppose the question is this, okay, that this is the partial tree given, okay, the question is that partial BFS tree is given. Now tell that what maybe next node to DQ or to pop. Okay, to DQ or to pop. Okay, tell me what may be the next node to pop or DQ. Okay, you can say maybe G, right? See, B must not be there in the queue, A must not be there in the queue, right? B and A obviously not there in the queue. Then maybe you're just exploring this G, right? Okay, and let's suppose see, if this is only the given, then can you say that C can be the next node? Can you say C can be the next node? See here, okay. Here, can you say that C can be the next node to pop out? Maybe, right? Maybe it depends that if G has already been popped out. See, if they only tell you this, okay, if they do not tell you any other information, and they only tell you this, okay, let's suppose they do not tell you any other information, they only tell you this, then you don't know whether G have been already popped out or not, right? So given this, do you know G have been already popped out or not? You don't know, right? Obviously you don't know. So you will say that maybe G is popped out, right? Maybe G is already popped out, and maybe G is not popped out. Maybe G is popped out and it doesn't have any neighbor. So that's why I'm currently in this state, right? So maybe G is already popped out, right? Is this correct? Is this correct? Then yes, this is correct, right? So the next node could be G, could be C, depending on the G is already popped out or not. Okay, depending on G is already popped out or not. So next node could be G or could be C. But let's suppose they modify the question. Okay, they modify the question. They say that suppose they say something like this. Okay, they say that it is given. Okay, it is given that G is in Q. Then among G and C, if I ask you what is the next node that is for sure will get pop out, then what is the answer? Among G and C. Okay, if they are saying G is already the part of Q, then what is the for sure you can say that will get popped out? Then G, right? Then G is the answer. Okay, in that case, then G is the answer. I hope you understood. If among G and C they are saying that okay, G is already the part of Q, then G is the answer, right? That is definitely going to pop out in the next iteration. Okay, so basically let's just continue now. Now you are going to pop out this G, and then you will say that okay, G neighbor is E and J. So that is why you will make E and J, right? Okay, so now I hope you understood that what is happening, right? E and J, and then I think you will go to C neighbor. C neighbor are already, I think, explored. Then you will go to E neighbors. E neighbors are K, right? E neighbor is K, and then this K is done, E is done. Then you will go to J neighbors, which is D and F, right? Okay. So I hope this is clear to everyone that how we are using BFS, and then what is the relationship between tree and the queue. Okay, this is important to understand, right? This is important to understand. Now you tell me this. This is going to be an interesting question. Okay, this is going to be interesting question. Okay, now you tell me this. Suppose if I say that given this, okay, suppose if I say that okay, this is, let's suppose, A, this is B, this is C, this is D, this is E, this is F, this is G, this is H, this is I. Okay, suppose if I give you something like this, right? So I can also write it inside, it doesn't matter, by the way. So this is, I think, D, E, F, G, this is H. Okay, so suppose if I say that that this is partial BFS tree is given to us, partial BFS tree, okay, is given. Suppose if I say, okay, so Raj is asking, well, PDF will be available or not? So yes, PDF will be definitely available. Okay, PDF will be available. So don't worry about the PDF. It will be available. So suppose if I say the partial BFS tree is given, which is something like this. Now you tell me, what are the possible nodes that are in queue. Okay, what are the possible nodes that are in queue? So let me have the options here. Suppose if I ask you, can C, which is a leaf, right? Remember, the C is a leaf. Can this C, okay, be the possible node? Can this E be the possible node? Can this G be the possible node? Can this H be the possible node? Can this I be the possible node? So C, E, G, H, I. Okay, C, E, G, H, I. I am just writing what are the possible nodes. So this is MSQ question. Can you tell me? Okay, is all correct? Is only E correct? Only GH correct? So what is the correct answer here? Can you tell me? This is little interesting question. Okay, just tell me what are the correct answers here. Okay, so Prashant is saying G, H, and I only. Okay, C and E are not possible. So that's what Prashant is saying. Unknown is also saying G, H, and I. Okay, and anyone else? Why the C and E are not possible? So by the way, are you guys Go classes student? Just wanted to ask. Okay, because I have already taught these things in the Go classes lecture. So just wanted to ask who have answered this, that okay, G, H, and I are possible, C and E are not possible. Are you Go classes student? Okay, those who have answered this particular question, just let me know. Okay, great. So unknown is saying he or she is a Go classes student. Okay, that's great. Now let's just see. Okay, Dijkstra is saying Go classes student. See here, this C and E must have been popped out. Okay, see here, this C and D must have been popped out. Let me just tell you what is the reason. Okay, maybe G is in the queue. Okay, you don't know. Okay, you don't know. Maybe G is in the queue, maybe H in the queue. But the C and E. Okay, this is E. C and D must have been popped out. What is the reason behind it? Okay. What is the reason? See here, you will in BFS, you will go level by level. You will pop out this A and then you will explore these neighbors, right? Then you will pop out this B and then you will explore its neighbor. Okay. So basically you will pop out this B and then you will explore its neighbor and then you will find out that okay, its neighbor are B neighbor is D and D, right? So let's suppose that you first pop out this A, then you will say its neighbors are B and C. Then you pop out this B and you say that okay, its neighbors are D and D. Right? Now, interestingly, now you're saying that the neighbors of D, can you directly explore the neighbors of B without popping out the C? can you directly explore the neighbors of D without popping out the C? No, right? So you must have to see after this B, who is the next? See A and then B and then C, right? I mean, A will, you will explore B and C. So basically you will pop out this B. Okay, you will pop out this B, you popped out this A, you will pop out this B. And now who is next? So basically in terms of Q, if I tell you, see, first you will push A, right? First you will push A. In terms of Q, if I tell you, see here, you will push A, pop out it, and then BC. Now pop out it and then D. See, can you explore this D? Can you pop out this D without even popping out the C? No, right? It is not possible. So you must have popped out the C, right? You must have popped out the C already. So that is why you will say you must have popped out the C, because it is level by level. Pop out A, explore its neighbors. Pop out B, explore its neighbor. Pop out C, then only you can pop out this D. If this D is already explored, okay, if this D is already explored, then it means you must have popped out the C, right? So that's great. Now you must have popped out the C, then only you can explore this D. And then if you are exploring this F, then you must have popped out this E also, right? The E is also not part of the Q. So basically what I'm trying to say, you must have popped out the C, then only you're exploring this D. Then you must have popped out this E, then only you're exploring this D, and then F and G. Then you must have popped out this F, then only you're exploring obviously H and I. And now in the Q, maybe G is there, maybe G is not there, depending whether G neighbors are there or not, or something like that, right? So basically in the Q, as you know, that G, H and I could be there, right? G, H and I could be there. So now you know the answer. What is the answer here? G, H and I. So this is the answer, right? Answer is G, H and I. Understood? Great. So now you know that what is the relation between this tree and the Q. Now, interesting phenomena here which is happening is that interesting phenomena here which is happening is that leaves are okay. See, I told you leaves could be the part of the tree, but not more than last level and the next last level. So only last two levels leaves could be there. Okay, last two levels leaves could be there. Other than that, this leaf cannot be in the queue. So only last two levels, because maybe you don't know, maybe you have popped out it, you don't have popped out, you haven't popped out it, like you don't know, maybe it doesn't even have the neighbor or not, right? You don't know this. So basically you can say that last two levels, I mean, if I just tell you this, okay, if I just write something like this, that given partial BFS tree, we can always say that all leaves are part of Q. Is this true? Is this true? If I just ask you true, false, is this true? Then you will say it is false, right? It is false. Now, if I ask you that given this partial tree, we can always say that only last two levels leaves may be part of Q, right? Last two levels, or instead of writing this all, if I say last two levels, so if I say last two levels, right? So here say that last two levels may be part of Q. Then what is the answer? Then the answer is true. Okay, last two level leaves, right? Last two level leaves. Right? Then the answer is true. Understood? Hope you understood. Cool. So basically this is false, this is true. Now I hope you understood that how this tree is or the BFS tree or the partial BFS tree and the Q relation is working, right? Okay. Now let's just go to this particular question that I have here. So what they're saying, suppose that vertex Vi and Vj are enqueued during the execution of BFS and Vi is enqueued before Vj. So they are saying D means distance from the root, okay? This is distance from root. Okay, so what they're trying to say is that suppose that vi and vj are enqueued during the execution of bfs, and vi is enqueued before vj. So they are saying vi is enqueued here and vj is enqueued somewhere here, right? Now does this mean that distance of vi, okay, from the root, okay, from the root, distance of vi is basically less than or equal to distance of vj? See here what does this mean? The distance of vi, right? It means that this vi, I mean, see here, let me just go to the next page. Let me just try to explain you that what I'm trying to say here is that, see, okay, see here, this is distance of vi, which means let's suppose I have this particular tree. So this distance is 1 from a, right? This distance is 1. Similarly, this distance is 1, this distance is 2, this distance is 2, this distance is 3. Okay, from a this is 3 distance, right? From a this is 3 distance, from a this is 3 distance, right? I mean, number of edges in between 1, 2 and 3. And from a this is 1, 2, 3, 4 distance, like that, right? So now you know what is the distance. Now what they're asking, that if you have enqueued this before, which means it must be the case, that you have explored. You are saying that okay, this is what I mean, this is what vi is. Now the vj, that means the vj in the next you are going to enqueue, so the vj could be on the same level. Tell me, can this be no same level? Can vi, okay, so basically it may not be directly connected, there may be multiple nodes in between, but don't worry about it. What I'm saying, that vi and vj, can they be on the same level? Maybe. Can this bj be here somewhere on the below level? Yes, maybe, right? But can this bj be on the top, I mean, before this bi? No, right? Vj cannot be here. So which means if I'm saying that if I'm enqueuing this vi first and then later on if I'm enqueuing this vj, it must mean, okay, see, this is the relationship between q and the tree, right? It must mean that I must have explored this vi first, right? Okay, so I must have explored this vi first. Now I'm going to explore this vj, right? Maybe on the same level, maybe I'm going to put this vj, or the vj is going to come maybe on the different level, right? Maybe on this level, maybe vj is here. So yes, this distance, if I talk about the distance, then this distance is lesser than or equal to vj distance, right? Okay, so suppose this question is saying something like this. Let's suppose if I have something like this, instead of lesser than equal to, if I just have strictly lesser, then will this be true or false? If I just have strictly lesser, tell me. In that case, will it be true or false? I am saying, if I'm saying that suppose that strictly it is on the next level, I'm enqueuing it later on, that's fine, but strictly it's on the next level, then what you will say? True or false? In that case, it will be false, right? So in that case, it will be false. So if it is strictly lesser than, then it will be, in that case, it will be false, right? But if it is lesser than equal to, then it is true. Maybe on the same level, right? Maybe on the same level, maybe on the different level, right? Okay. Now let's just solve this question. So what they're saying, suppose that during the execution of BFS, the queue contains this, okay? Queue contains these vertices. So they are saying there is a queue, okay? There is a queue which contains V1, V2. Currently it contains V1 to VR. V1 is the head of queue. Okay, V1 is the head of queue. Then what can you say about the distances, right? So they are saying that you have V1 to VR and V1 is the head of queue. So is this true? That's what they're asking, right? Interesting question. It is. Tell me. By the way, this question I have taken from Corman. Okay, Corman question. This is a question from very, very standard book, which is Corman. For algorithms, this is top-notch book. Now you tell me, which is the correct answer, this or this? I mean, both are true, only one is true. What is the case? So this is V1 to VR. What you will say that, okay, Vi, what is the relationship between the immediate two vertices? Yes, this is the correct relationship, I think, right? This is the correct relationship. So which means that this Vi And this vi plus 1, if I talk about bi and bi plus 1, can they be on the same level, or maybe the bi plus 1 is the next level or something like this? That's what we have seen, right? So yes, this is true. And what about this? This is interesting. What about this vr? Okay, this vr and v1. So they are saying if that is the case, then this v1, okay, so here if you see here, v1 is the head of q, okay, and vr is the tail. Now they are saying that this is the relationship between vr and v1. So v1 is some vertex, that is the current state of the q, I think. Okay, so v1 is some vertex, and then vr is some other vertex. Now they are saying that vr, okay, vr is basically strictly lesser than equal to v1 plus 1. v1 plus 1, I mean, which means it cannot be on the same level. Okay, v1 and vr cannot be on the same level. What about this? Just let me know. See, if nothing is given here, right? If nothing is given here about v1 and vr, they are saying they cannot be on the same level. You don't know. Maybe they can be on the same level, right? They can also be on the same level, right? So in that case, it is false, right? They can be on the same level. But let's suppose they say that b1 is root, okay, root of BFS tree. Then obviously this must be 0, right? This must be 0. If they say that b1 is the root of the BFS tree, then distance to b1 is 0. Then okay, so what they're saying, okay, this is v1, right? Yeah, then also it is less than equal to 1. Then it is not I mean, okay, I'm just making it unnecessarily complex. By the way, this is false, right? This is false. Okay. Okay. So someone is asking my name. Okay, let me just introduce myself. I'm I'm Sachin. I'm Sachin Mittal, right? I have achieved All India rank 33, and I am ISC pass out, ISC MTech from CSA department. I have also worked at Amazon as an applied scientist. Right? Okay. And I'm also co-founder at GoClasses. Okay. Now let's just talk about the BFS edges, right? BFS edges. So basically, if you have seen the previous video about the DFS, then we have told you that there are different type of edges, right? Cross edge and these things, right? Now let's just talk about the BFS edges now, right? So here in the directed case, we have 3 type of edges, and in the undirected case, we have 2 type of edges. Let's just see what are these. Okay. So suppose I have some BFS tree. Okay, let me just copy this tree as it is. Okay. So suppose I have some BFS tree, and let's just think of this tree as a layers. Okay, let's just think of this tree as a layers. So let me just say that this is, okay, the first one is a layer 1 and so on, right? Let me just think of this tree as a layers. So what do I mean by that? Let me just tell you. See here, let's suppose this is the layer 1, this is layer 2, okay, this is layer 1, this is layer 2, and so on, right? Layer 2, this is BFS tree. Now this is layer 3, this is layer 4, this is layer 5, and so on. Okay. Now suppose you have this as layers, okay, right? This is, let's suppose, layer 1, then maybe the layer 2, right? And then maybe layer 3, then maybe layer 4, and so on. So what I'm saying here, this is BFS tree, and now I'm thinking of this BFS tree as a layers. This is root, maybe these are the multiple neighbors. This is something like this, right? So I'm thinking of this BFS tree as a layers. Is this okay to everyone? Now let's suppose that I say, if I just ask you, okay, this is the BFS tree. If I just ask you, in the graph, see, in the tree I'm not talking about. In the tree there are only tree edges, right? You might have heard about the tree edges from the previous discussion about the BFS, DFS. Okay, if you don't know this particular video about this particular video, then I will suggest you to go to the YouTube and then search about the DFS, right? I mean DFS Go classes. So maybe if you search DFS Go classes, let me just put it here for you, then you will see this particular video, right? So you should watch this video. This is very interesting and very nice video. So you can just watch this video, right? So if you search about this DFS Go classes, you will be getting this particular link. Now let me just tell you that there has been many good comments about this particular video, right? There has been many good comments about this particular video. So I can also put the screenshot of the comments. Right? Have you seen that video? How many of you have seen this DFS video? Okay. So you can definitely watch this video, right? To understand more about the edges and all. Now, what I'm saying here is that in this, if I just think of this particular thing as a layers, then you can assume that okay, this is layer 1, this is layer 2, and so on. Now there are only tree edges in the tree. In the tree there are only these kind of edges. These are called tree edges, right? In the tree there are only these kind of edges. Now tell me, can in the original graph, right? In the original graph, if I ask you, can there be the edges like this? Okay, can whether it is directed or undirected, let's suppose it doesn't matter. But if I just ask you, can there be in the original graph, can there be an edge like this? If it is directed, then can it be like this? In the original, okay, in the original. See, in the tree there is only these tree edges, but in the original graph, can you tell me, can there be the edges like this? If there is a edges like this, okay, if there is a edges like this, then do you think that this kind of BFS tree have been possible? What do you think? No, right? So if there's edges like this, then obviously this kind of BFS tree have not been possible. What is the reason behind it? Because see, if there is something else like this, then this particular node, right? This particular node must have been here, because this is never, right? See, if this is the edge which is possible in the original graph, then this particular node must have been here, isn't it? So this kind of edges are not possible, and these are called forward edges. Okay, with the definition, these are called forward edges, right? Okay, so these are called forward edges. So basically this edge is called forward edge. Now I can definitely say that this kind of edges, which is called forward edge, why it is called forward edge? Because it is from ancestor to descendant, right? It is from ancestor to descendant. That is why it is called forward edge. So the forward edge is not possible, right? Forward edge is not possible, right? Understood? So in BFS, the forward edge is not possible. Okay. Can this kind of edges be possible? Can the back edge be possible? Can the back edge be possible? Tell me. Can this kind of edges be possible? Back edge. Just think about it. Can the back edge be possible? Then the answer is yes, right? So back edge is possible. Okay. Why? Because see here, in case of directed, the back edge is possible. Why? Because it is definitely possible that you explore this, and then you explore this, and then later you found out, oh, okay, you explore this neighbor, and then later you find out that it is connected to this, right? It is connected to this, right? It is connected to this. So definitely it is possible. So back edge is possible in case of directed. Okay, in case of directed, the back edge is possible. So I can say that back edge is possible. Okay, back edge is possible. Now tell me the same case in case of undirected. Now tell me the same thing in case of undirected. Can this kind of edges be possible in case of undirected? See, in the tree it is obviously not there. In the tree there is only tree edges, right? These are the only tree edges. But in the undirected graph, in the complete or in the original graph, can this kind of edges be possible? Then the answer is no. This kind of edges are not possible. In the undirected graph, neither forward edge nor backward edge, nothing is possible, right? Forward and backward edge is not possible. No. So no backward edge in undirected. In undirected. Understood? Okay. So here, see here that if you think of this as a layers, then it is very easy to understand this edges, right? Now you know that, okay, in case of directed, this kind of edges is not possible, but this kind of edge is possible, right? In case of undirected, this edge is not possible. Okay. Now you tell me about the edges within the level. Okay, this is the edge within the level. Is this kind of edge possible? Is this kind of edge possible? Think about it. Is this kind of edge possible? Okay, in directed or undirected doesn't matter. It is possible, right? You can definitely explore this, and then you later on find out. Okay, I mean, so basically you can say that in case of directed, maybe this is the edge, right? Maybe this is the edge. So you can say, okay, let me explore its neighbors, right? Its neighbors. Then if you go here, you will explore its neighbors. You go here, you found out, oh, that was already connected. So that is definitely possible. So in case of directed, this is possible. In case of undirected also, this is definitely possible, which means in case of undirected also you can say this is definitely possible. Why? You will go here, you will explore its neighbors, and then you explore this first, then you will go here, then you will say that, okay, this is already there, I mean, it is already connected. So the cross edge, this is called cross edge, right? So the cross edge is possible, which means, don't worry, I will just compile all the things what I'm trying to say, but first understand here what I'm saying is that this kind of edge, right? This kind of edge, which is called cross edge, which means within the layer, okay, within the layer edge is possible, but this skip edge is not possible. Okay, skip edge is not possible, right? Okay, skip, I mean, if you're skipping the level, then it is not possible. Now you tell me, is this possible? Is this possible in case of directed or in case of undirected, whatever, right? Is this possible? Is this possible? So this is called cross edge. In case of directed, yes, you will explore this. I mean, you will go here, and then you explore this. You will explore this like this. Then you will say that, okay, this is already explored, right? So this cross edge is possible. So cross edge can be of two types. One is within the label. Another one is across the contiguous labels. Okay, one is within the label, another one is across the contiguous labels, which means this kind of edge. So these are called cross edges. So cross edges are possible in directed and undirected both. Okay, so here what I'm trying to say here is that this kind of edges is possible in directed. In undirected, this is not possible. In directed, this is not possible. And see, this kind of edge, skip level edges are not possible. If I talk about cross edge, then undirected, this is also possible. In undirected, this is also possible, right? This is also possible. In directed also, this is also possible like this. So the cross edge, either of this kind or maybe of this kind is possible, right? Cross edge is definitely possible. Understood? Now, what is remaining? I think back edge we have covered, right? I mean, back edge is not possible in undirected. In directed is possible. Tree edge, cross edge, and what is the other thing? So there are 4 types of edges. What is the other thing? Forward edge, right? So the forward edge, which means from here to here, is this possible? We have already covered that this kind of edges are not possible. So forward edge is not possible, right? Forward edge is not possible. So let me just summarize everything. Okay, let me just summarize everything. Let me just ask you, if you have not understood anything, don't worry about it. Let me just quickly ask you this. Suppose if I say, okay, if I say something like this, this is given, right? If I say okay, or maybe let me ask you, forward edge is possible in directed, yes or no? In undirected, yes or no? You just need to tell me. Okay, in directed, in undirected. Just tell me. Forward edge means going from ancestor to descendant. Okay, going from ancestor to descendant. Is this possible? This is ancestor, this is descendant. So maybe this or something like this. Is this possible? In case of directed, is this possible? In case of undirected, this is possible. Yeah, great. So no and no, right? Okay. Now let me ask you another question, which is tree edge is definitely possible. And let me ask you back edge, right? Back edge. Now again, the question remains same, which means in case of directed, is this possible? In case of undirected, is this possible? Okay. So tell me here, the question remains same. In case of directed, is this possible? In case of undirected, is this possible? In case of directed, what do you think? The back edge means going from descendant to ancestor. Descendant to ancestor. Is this possible? Directed, yes. What about undirected? Going from descendant to ancestor? No, right? No. Okay. Okay. So what is the last edge that we have? Cross edge, right? Cross edge. Now you tell me the cross edges. In case of directed, is this possible? The cross edge means from here to here, or maybe, sorry, not from here to here, from here to here like that, right? Maybe within the label, skip label or like that. Maybe this, right? Maybe this. In case of directed, yes. Undirected, yes, right? I mean, it doesn't matter. Let's suppose this is the edge, then maybe it is possible, right? I mean, directed and yes, undirected, yes. Okay. Okay, great. What about my last question, which is basically saying the tree edges? Tree edge. Obviously, tree edge is definitely there, right? These all are the tree edges. So yes and yes, right? Tree edge is definitely there. So I hope you understood that what I'm trying to say here, right? So these are the answers. Now you understood very well that that given this, I mean, you don't need to remember, okay? You don't need to remember this particular thing, which means you don't need to remember the type of edges and so on, right? So given some, let's suppose question, okay, just like that okay, in undirected this is possible or not, you just make, what is the first step? Make this skips, make this labels like this, okay? Make this labels like this and then understand. So understand DFS like a layers, okay? Layers. Understand BFS like a layers. So these are also called BFS layers, okay? BFS layers. Understood? Okay. Now, do you need to remember this? Do you need to remember all of this? So the answer is no, don't do it, okay? No, don't do it. What you need to do, instead of remembering this, just make something like this. And now, can you quickly answer all of this? Okay. Is the tree edge possible? Yes, right? Is the cross edge possible? Right. Yeah, cross edge is possible here also. Is the back edge possible in the directed? Back edge, yes, it is possible. In undirected, is this possible? No, right? So given, you just draw layers, you just draw the layers and then answer all of this. Okay. After drawing the layers, you can definitely answer. Now, let's just see what they have written here. Let's just see, right? Okay. I hope you can see my screen. This is layers. Okay. So you can see the screen, right? So can we have an edge? Okay. This is the question from Washington University. So what they are saying, can we have an edge that goes from layer I to I plus 2 or lower? So they are saying that this is, let's suppose layer I, this is layer I plus 2. Okay. So can we have this edge? So this is basically, they are talking about the forward edge. So they are talking about the forward edge, right? This is not possible, right? The forward edge is not possible. So they are talking about, so answer is no also. So this is, they are talking about the forward edge. Okay. Now, what is the next question? Can you have an edge within the layer? So answer is yes. Within the layer means they are talking about which kind of edge? Cross edge. Cross edge. So forward edge, no in both the cases. Cross edge is yes in both the cases, right? I mean, they have, even if they have not given whether it is directed or undirected, it doesn't matter. Forward edge is no in both the cases. Cross edge is yes in both the cases. Yeah, cross edge is definitely possible from any level to any level. So this is also the cross edge. Okay, Prashant is asking, is this also cross edge? Yes, this is also the cross edge, right? The definition should be clear. So what is the definition of this cross edge? It is basically saying that between two vertices which doesn't have any relationship of ancestor and descendant. So this and this doesn't have any, neither this is descendant of this, nor it is ancestor of this. Okay, if doesn't have any relationship of descendant and ancestor, then this is called cross edge. Okay. Now let's just answer this question which have been asked in GATE 2015. Now what they are trying to say, let's just see. Okay. Now you should be able to answer this question, which is very interesting question, which have been asked in GATE 2015. Now what they are saying is that let G be a simple undirected graph they are talking about, right? Now as we have particular vertex and it is called a source. Okay. So they are saying that you have some undirected graph. Okay. Let me draw the layers if that is required. And then they are saying that you start with some source. Let's suppose this is some source S, right? Now dx denotes the shortest distance in G from S to X. The BFS is performing starting at X, S, okay? Let T be the resultant BFS tree, okay? So let's suppose this is the T. If UB is an edge of G that is not in T, okay? So suppose UB is some edge, okay, which could be, what kind of edge it must be? If it is undirected graph, then it must be, see, the forward edge is not possible in both the cases. In undirected, back edge is also not possible, tree edge is also there, is always there. So the cross edges must be there, right? This must be the cross edge. Okay, is an edge in G, then which of the following cannot be the value of DU and UV? So they are saying that the cross edge. So cross edge means it could be something like this, right? Cannot be the value. Okay. Yeah, this is interesting. Can you try to solve this? Okay, by the way, yeah, this escape level is also not possible, right? See here, I think I have told you that this kind of cross edge is also possible, but this kind of cross edge is also not possible, right? This is a cross edge, but this kind of cross edge is also not possible. So here in the BFS, the cross edges could be this type, I mean, could be this, or maybe this, right? Maybe this. But if you have something like this, then this is not possible because you will definitely put it here, right? You will definitely put it here. Okay. So see here, that what I'm trying to say, that here in the BFS, this kind of cross edge, this is a cross edge that I agree, but this kind of cross edge is not possible. Why that is the case? Because if that is the possible, see, you will go here, you will explore its neighbors. That is possible because that is already explored, right? I mean, once you go here, you will explore its neighbors. But since this is still unexplored, that is why this escape kind of edges is not possible, right? Escape kind of edges is not possible. Okay. So in undirected or directed, whatever it is, this kind of cross edge is not possible. So which means if this is U, this is V, can you say the distance between U and V, how much it should be? So the difference between DU and DV, okay, for the cross edge, it could be 0, which means the cross edge is on the same level, or it could be 1, right? Could be 1 or -1 means that U could be this, or V could be this. So could be 0, could be 1, could be -1. Which means if the question is this, right, then what is the answer? The cross edge is possible, but this kind of cross edge, or maybe this kind of cross edge, but this kind of cross edge is not possible, right? So what is the answer here? -1 is possible. -1 basically just mean that, okay, maybe this is U, this is V, right? -1 just mean this. 1 just mean that, okay, this is U, this is V, right? 1 just mean this, right? So basically it could be -1, could be 0, could be +1. Basically, I mean, it should be less than equal to, you can say 1, right? I mean, within this, less than equal to 1, and basically, I mean, you can say, okay, it can take -1, 0, 1, 3 values, right? So 2 is not possible, right? 2 is not possible. So D is the answer here. Now suppose they ask you the same question about the directed graph. Okay, instead of undirected, they say directed graph. Then what you will say? Then what you will say? If they say directed, then is this 2 possible? Then this 2 is possible, right? Maybe this is a back edge, you don't know. So cross edge or back edge, it could be the cross edge or it could be the back edge also, right? So maybe this is a back edge, you don't know. So that is why cannot be the value. So maybe this can be the value, this can be the value, this can be the value, this can be the value. So cannot be, or if they say, let's suppose they say can be the value, right? Instead of cannot, they say can be the value. Then what is the answer? And let's suppose this is MSQ, right? Let's suppose they form this as MSQ and they say can be the value. Then what is the answer? Then answer is all. Okay. Then answer is all. Okay. Now see here, if you are still having confusion, tell me, is backhash possible from here to here, from any level to any level? Yes, right? Because you may be exploring this, maybe exploring this. So backhash is possible from any level to any level, right? So backhash is possible. Backhash is possible from any level to any other level. But tell me, is the crosshatch possible? Is the crosshatch possible? Crosshatch means okay. So in case of directed, actually the crosshatch, this kind of edge is possible, right? So tell me, is this as possible in case of directed? Is this possible? Possible in directed? Then what is your answer? The answer is yes, right? This is a cross edge. This is a cross edge and it is possible in directed. But if I ask you the same question, is this possible in undirected? If I ask you the same question, is this possible in undirected? Then your answer is no, right? No. Skip label cross edge is not possible. Skip label cross edge not possible. Okay. Now let's just ask a question. Let's just see if you can answer. So this is a question which is bit hard. Okay, this is a hard question. Let me just ask you. Suppose we have an undirected graph, which has a cycle of let's suppose I say odd length, then it has cross edge. I mean, I'm talking about the BFS, right? So it has BFS cross edge option A within same level, option B within or across two consecutive levels. Okay. C across skip levels. D does not have crosses. Can you tell me what is the answer? What I'm saying here is that suppose we have an undirected graph which has a cycle of odd length. Okay, so they are saying So they are saying, let's suppose you have the BFS tree, you have the cycle here, which means the cycle could be like this, right? Cycle could be like this. I mean, in the original graph, cycle could be like this or something like this, right? So there's a cycle in the original graph. They are saying that the cycle is of odd length. Okay. First of all, tell me, does this necessarily have the cross edge? Does this necessarily have the cross edge? See, if there is a cycle, okay, if only tree edges are there, then what is the how you can have the cycle, right? It must be having the cross edge, because either tree edge is possible or the cross edge is possible, right? In undirected. So basically you can say, if there is a cycle, then it must be having extra edges. Those extra edges are the cross edges. Now they are saying it must be having the cross edge. That is for sure, because you're undirected either tree edge or cross edge. Okay, or if it is forming cycle, then it must be having extra edge. Okay, does not have cross edge, so this is the wrong answer. I mean, it must be having the cross edge. Now the cross edge across skip labels, this is not even the possible, right? This is not even possible in undirected. So that's why C is false. C is false because it is not possible. Okay, false because in undirected it is not possible. D is false because extra edges are there. What about B? Across two consecutive levels or within the same level? It must be having the cross edge. That is for sure. But across, if it is odd length cycle, see, if it is odd length cycle, then is this kind of edge or this kind of edge? That's the thing they are asking. See, if it is odd length cycle, then you can see that this is 1, 2, 3, 4, 5. Then within the same level, right? Because if you have across this level, across two consecutive level, then this is even length cycle you are forming. Okay, this is even length cycle you are forming. So that is why you can say this is across two within the same level, right? Within the same level. So A is the answer. Yes. So most of the people have given the correct answer, right? So A is the answer here. Why? Because it is odd length cycle. And now maybe the cycle is here, which means if it is odd length, then it must be within the same level. Why? Because let's suppose these are the x number of edges and this must be the x number of edges. So the extra edge is 1, right? So total edges will be 2x plus 1 in the cycle. But if it is okay, not within the same level, if it is across the level, then what will happen? If it is across the level, okay, let's suppose this, then this is x number of edges, right? This is x number of edges, you can say. This is x number of edges. And this is also the x number of edges, right? I mean, including this dotted edge, there will be 2x edges in the cycle, right? So there will be 2x edges only. So which is even length cycle, even length. Okay, even length cycle. So it must be within the same level. So here, let's suppose if someone asks you that undirected graph has BFS cross edge, then there must be cycle. Then what you will say? What you will say? Then the answer is yes. Then the answer is yes, right? Yes. Understood? Let me know. Okay. Undirected graph has BFS cross edge, then there must be a cycle. What is the answer? Yes. Okay. If someone says that undirected graph has even length cycle, then cross edge must be across the levels. Okay. Cross edge must be between two levels. False or true? Tell me. This is even length, right? So this is true, right? Why that is true? Because you can see here that for the even length, if this is even length, okay. So if it is even length, then it must be across the level. Then only it will be 3 and then maybe 3, right? 6. Okay, if it is even length, then across the levels, right? This is true. Understood? Okay. Anyway, like this is the little introduction of the BFS that we want to do. Okay. Now let's just see this BFS for the shortest path in unweighted graph. Okay. So we will now see the BFS, how this BFS works in the shortest path. I mean, as a shortest path for the unweighted graph. For example, let's just consider one example here. Suppose you have some unweighted graph. Okay. Okay. Let's suppose this is A, this is B, this is C, this is D, this is E, this is F. If you run DFS, depth first search, if you remember DFS, then let's suppose you're starting with A, maybe it can go to B, it can go to then D, then it can go to F, then E, and then C, right? So which means it is possible that DFS will do something like this. But if you do BFS, okay, then it will go to the neighbors only, as we have seen, A to B and C, and then and then F also. Okay, whatever the neighbors, it will explore all the neighbors, right? Whatever the neighbors, it will explore all the neighbors. So A to B and C and F, right? All the neighbors, and then B, C and F is done, and then it will go to B, and then it will explore D, and then from C it will explore E, right? This will be BFS. Now you notice one thing, that this DFS is tall and skinny, and it is possible that DFS is giving you, okay, that A to F. Okay, if you see the A to F, DFS is giving you 1, 2, 3, right? It is saying 3, but BFS is always giving you 1. I mean, it is directly reaching because it is neighbor, isn't it? See, it is giving you 3, it is just giving you 1. Understood? So that's why what you will say, it is giving you 3, it is giving you 1. So you will say that DFS may not give you the shortest path, but in unweighted, BFS will always give you the shortest path because it is going to all the neighbors. Okay, that's why it is saying that, okay, whatever the shortest, and then from this B, all the neighbors, right? So basically in unweighted, if the graph is unweighted, okay, in unweighted graph, unweighted, BFS works as short, right? But suppose the graph is weighted, which means suppose this is the case. Suppose the graph is weighted. Suppose this is C. Let's suppose this is 100, this is 1, this is 1, this is D. Okay, something like this. Then BFS will say, this is the BFS tree. What BFS will say? BFS will say that, okay, this is A, and from this A, I will go to B, and then from this A, I will also go to C, and then from this A only I will go to D. So A to B is 1. BFS will say that A to C should be 100, isn't it? Let's suppose this is 2. So this is the shortest it is giving. Is this correct shortest? See, if the graph is weighted, BFS doesn't even care about the weights, right? So if BFS is saying this is the shortest, which is wrong, right? So BFS gives, or may give, you can say may give wrong shortest in weighted, right? So it is basically in unweighted graph, in unweighted you can say, in unweighted for sure you can say BFX works as a shortest path algorithm. Do DFS also works as a shortest path? No, right? DFS may pick this B, and then if you explore using this B, then it will be a disaster. I mean, you will not be having the shortest path, right? Because shortest is direct. Okay. Now let's just try solving some questions, okay, that they have asked. So maybe you can solve this question. Actually, you will get to understand this Dijkstra and Worzel algorithm and these things, okay, in the coming slides. But for now, can you try solving this question? What they are trying to say is that, so they are saying that you have undirected, okay, and unweighted graph. Okay, you have undirected unweighted graph. The shortest path from S to every node is computed most efficiently. Actually, BFS is basically just like BFS time complexity. It's just like DFS. Okay, I have explained this DFS very clearly in the previous video. So you can see the DFS previous video. Maybe I can just tell you which one. See, you can see this video for the time complexity. Okay, I'm not going to tell you again, but you can see this video. The time complexity is order of V plus E. V and E are the number of vertices and the number of edges respectively, right? Okay. Now coming to this. So what you will say, Dijkstra and floor reversal, these are good algorithms actually, but this can definitely compute the shortest path, but this is heavy. Okay, this takes more time. Okay, takes more time. We will see later on, but takes more time. Okay, perform BFS. Perform DFS. Is DFS can be performed and you can find the shortest path? Then no. Can this be performed? Yes, but takes more time. They are asking about the most efficient algorithm. Okay, it takes actually lesser time. We will compare the time complexities later on, but for now you can see here that it takes the lesser time. So that's why D is the correct answer. Performing BFS, right? Performing BFS. Okay. Now maybe just a second. Yeah, so let's just go to this question. Okay, let's just go to this question and let's just see what is the answer here. Can you tell me what is the answer here? So what they're saying is that consider the BFS traversal, okay, of unweighted graph or undirected graph, the tree formed by the arc data structure by computing. Okay, will you give the shortest path between every pair of vertices? It will give the shortest path. Let's suppose you are starting with W. Okay, source node is W. It will give the shortest path between every pair of vertices. Do you really think? Let's suppose this is A, this is B, okay, this is C, right? And then this is D. Okay. Now suppose you perform BFS here. Now what is the answer of BFS? It will say ABCD, right? I mean, from this A, it will say B, C and D. It is not even telling you any relationship between B and C, or if you like to treat it as a undirected also, then I mean basically the tree we generally consider as a rooted tree here. Okay, anyway, like let's not go into the graph theory. Basically the graph may not be having the directions, but tree is a rooted tree, which means it is having the directions. Anyway, it is not telling any path between B and C, right? Any path in between B and C. So it may not tell between every pair of vertices, but it will tell from the source vertex to every other vertex. Okay, so shortest path between every pair of vertices, do you think? No. The shortest path from W to every other vertices? Yes. Shortest path from W to only those that are of leaves? No, that's not like that. So basically B is the correct answer. B is the correct answer. The longest path in the graph? No, it's not like that. So do I have the answer? Okay, I don't have the answer currently, but yeah, B is the correct answer. Okay, from source, this is called single source shortest path. Okay, single source shortest path, which is from one source to every other vertex. For example, let's suppose I have little complicated graph. Let's suppose maybe I might be having some graphs here and there. I can quickly pick one graph. Just a second. Okay, suppose this is the graph that I have, right? Okay, so now let's just see how BFS is giving you shortest path, right? So you start with this A. Let's suppose you start with this A. Then you will go to B. You will go to G. Now let's just see that what happens if you go to this B. You will go to C, and then if you go to this G, then you will go to E and J. This is E. This is J. Then you will go to C. I think that is fine. Then from this E, you will go to K, J and K. Let me write in alphabetical order. J and K. and then from this j, sorry, j is already explored, so you will go to only k, right? And then this is done. I think from this j you will go to d and f. Okay, so this is the shortest path from A only, which means from A, if you want to go to F, then if it is unweighted, then the shortest should be this. Okay, A to G. Okay, A to G, and then G to, since you are going to neighbors, then this is the shortest from A to F, right? Is this also telling you the shortest from D to F? Okay, or something like this. From D to F, it is direct edge. It is not even telling that, okay, there is a direct edge or something like this, right? Okay. So what about the question 27? Which one? The shortest path. Okay. So is this clear or there is some problem? Let me know. Yeah. Okay. So here B is the correct answer. Now I hope you understood that here the shortest path is from A to every other node, right? From from A to every other node, which means it is called single source. Okay, single source shortest path. Single source shortest path. Okay, let me know if that is clear. Okay. Now let's just solve more questions regarding BFS. Now what they are saying, let's solve this question. So what they are saying is that this question has been asked in GATE 2016, right? This question has been asked in GATE 2016. Let's just solve this. So what they are saying, that the BFS is started, okay, is started at the binary tree beginning from the root vertices. There is a vertex T, there is a distance 4 from the root. Okay, they are saying that there is a vertex T at the distance 4 from the root. Okay, so which means if this is root, then from here at the distance 4 there is a vertex, okay, which is T. If T is nth vertex in the BFS traversal, then the maximum value of n is. Yeah, that's a good question. Can you try solving it? Let me know what is the answer you are getting. So, okay, answers are not on the next page. You just tell me what is the answer you are getting. They are saying this is binary tree. Okay, and they're asking about the maximum value. Okay, they are saying it is binary tree. So see here, this question can be done very easily, right? They are saying it is a binary tree and it is at the distance 4, right? It is at the distance 4. So which means there will be a source, and then since it is a binary tree, okay, then it could be 2 and 2. So basically this at the distance 1, 2, 3 and then 4, right? So at this level it is, right? Now where it can be in worst, it can be at this level. I mean, it can be the rightmost basically, right? So basically they are saying that what is the possible value of n? What is the possible value of n? Which means that how many nodes are if this is the nth vertex. So basically how many nodes are there total? Which means this is 2 power 0 node, this is 2 power 1, this is 2 power 2, this is 2 power 3 nodes, right? Which means 1 plus 2 plus 4 plus 8. 0, 2 power 1, 2 power 2, 2 power 3, and this is 2 power 4, right? 8 plus 16. So which is coming out to be 31, right? Which will be 31. So see what they are saying, that it is a binary tree and there is a vertex T which is a distance 4 from the root, okay, which means it must be at this level. So what is the maximum possible value? Maybe this is the vertex, right? Maybe this is the vertex they are talking about. They are saying that this is at the distance 4, distance 1, 2, 3, and then 4, right? So basically it must be, this is a binary tree, by the way, okay, which means that at one level there will be two nodes only. At this level there will be 1, 2, 3, 4 nodes and so on, right? Because this is a binary tree, okay? But I'm not making all the nodes. So see, they are saying that the node is at this level, right? Node is at this level. So this is let's suppose first level or the 0th level, or whatever you want to say. Okay, let's suppose this is the 0th level. Let's not worry about the numbering here. Basically the distance is 4, right? So basically this distance 1, 2, 3 and 4, the distance is 4. So the node must be at this level, right? The node must be at this level because the distance is 4. Now they are saying what is the maximum possible value that this node might have been explored, right? What is the maximum possible value? So see, you can say that this node could be this node they are talking about could be this, could be this, could be this, could be this, could be this. So if this is the nth node that you are talking about, right? This is the nth node in the BFS traversal. Then what is the maximum possible value of n? This is the first node, this is the second node, third node, fourth, fifth, sixth, seventh, like that, right? So basically, if they are talking about the maximum possible value, then this is the maximum possible value. So which means the node must be here, right? So which means like including this, what are the total nodes? Because this is the nth vertex they are talking about. So this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So this is 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3 plus 2 power 4, which is coming out to be 2 power 5 minus 1, which is 31, right? Yes, we will definitely do operating system session also. Okay. I hope you understood, right? So 31 is the correct answer. What is the minimum possible value? For the minimum possible value, you will say till now, how many nodes are there? 16 nodes, right? Till now, I think, 15 nodes are there. And then this is the 16th node. So minimum possible value, minimum, this is 16th node. So 16, maximum, this is the 31st node, right? So 31. Okay. Understood? Now let's solve more questions. Okay, so this is GATE 2001 question. Let me just put the link here. I mean the screenshot again, because this is not much visible, right? Okay, just a second. So can you tell me what is the answer here in this particular question? Okay, so for the minimum, I think minimum could be more interesting. So the node, if it is at the level 4, then if it is at, after the 4 distance, the minimum, it must be this, right? Yeah, so basically it must be 16. Okay, if it is not balanced, yeah, it should be balanced, yes. For the minimum, it should be balanced. I mean, then only 16 is the answer. Yes, it is a good observation. If it is skewed, then you are right. If it is skewed, then it could be 1, 2, 3, 4, 5. Yeah, if it is skewed, then it is 5, right? That is correct, right? Because they have not talked about here whether it is balanced or not. Yeah, it is skewed. It could be skewed also, right? So I'm assuming that it is balanced. Okay. Okay. I mean, fully balanced. I'm assuming that it is fully balanced. Okay. Now let's just see this. Consider an undirected, unweighted graph. The BFS traversal of G can be done starting from node R. Distance from R to U and R to B with the length of the shortest path from R to U and V respectively. If U is visited before V, okay, if U is visited before V, then which of the following is true? So they are saying if U is visited, okay, they are saying that U is visited, then let's suppose this is U before V. So V must not be at this level, must not be at this level. So V could be at this level, right? Or we could be at later level. I think we have already done this, right? We have already done this question. Can you tell me what is the answer? So the distance to V could be equal also, or could be greater also. It cannot be, okay, it need not to be strictly greater, right? And cannot be lesser also. So basically what is the answer? Tell me. Answer is C, right? Answer is C. So this was a Corman question by the way. Right? This was a Corman question, right? And we have definitely solved it. Now let's just see this question. Okay. So what they're trying to say here is that consider weighted undirected graph with the positive weights, right? Now they're saying let UB be the edge in the graph. It is known that shortest path from the source to vertex S to U, the shortest path has 53. Okay, this is note that this is a weighted graph. Okay, this is a weighted graph. Now they are saying there is a weighted graph and the shortest path is given to you is basically S to U is 53 and the shortest path from S to B. So basically this is not about the BFS, by the way. This is a general question. Let me just tell you what they are saying. They are saying from S to U it is given to be 53. It is weighted undirected graph with a positive edge weights. Okay, so this is 53. Now they are saying from S to V, maybe V is on the same way or maybe other way, doesn't matter. So S to V they are saying is 65. Now they're asking about the weight UV. So UV is an edge. Okay, UV is an edge, right? This is one edge. Okay, this is the edge in the graph. Edge. Now can you tell me, this is the shortest, okay? It is given to be shortest. This is given to be shortest. So these are the shortest. Now suppose this edge weight is, let's suppose 2. Is this possible to have this edge weight at 2? No, right? Otherwise the shortest will be lesser, right? The shortest will be just 54. Can it be 12? Can it be 12? It can be 12, right? It can be 12. But can it be 11? Can it be 11? If it is 11, then the shortest will be 64 only. So basically, it can be 12 or more. So greater than equal to 12, right? Greater than equal to 12. Easy question. Right? Easy question. So C is the correct answer here. Basically, yeah, Ajay is right. I have given this type of question, okay, in our test series, and that is in the computer networks I have given in distance vector routing protocol. In distance vector routing protocol, I have given this type of question. Okay, in distance vector routing protocol, I have given this type of question. Anyway, don't worry. We will see those type of questions in the computer network sessions. Okay. Now, I think this is all about the BFS that I have here. Okay, समझ में नहीं आया? Let me just explain this again. See what I'm trying to say. This is given to be the shortest. Okay, this is given to be the shortest. This is also given to be the shortest. Right? These two are given to be the shortest. Right? These two are given to you as a shortest. Now they are saying that this is an edge. This is also given. This is edge. So these things are given to you. That this is the edge. Right? This is the edge. It is given that they are saying that see here that UV is an edge. Okay, they are saying that UV is an edge. They are saying this UV is an edge, right? Just read it here. Now what could be the edge weight of this? Can it be just 2? If it is 2, then this is violating the property that H2B is shortest, because otherwise the H2B will be 54. I mean 55. You can go like this. If it is 65 is shortest, then it cannot be 2. Can it be 20? Yes, maybe it is 20 because it is not violating any property. Can it be 12? Maybe. And can it be 13? Maybe, because it is not violating any property. But can it be 10? If it is 10, then it is a problem, because otherwise the shortest will be 63 only. Right? Shortest will be 63 only. If it is 10, then this is a problem. Okay, so it cannot be 10, 11 or something like this. Can it be 12? Yes, because the shortest is 65, which is fine. I mean, the shortest they are taking, like, I mean, there could be 2 shortest also, right? This and this, there could be 2 shortest also. It can be 12. It can be more than 12 also. Okay, this is, by the way, it's also called triangular property. Okay, triangular property. Anyway, you don't need to know about the property name, but if it is this is shortest, then this particular thing is basically could be 12 at most. At least it should be 12. Okay. Now let's just talk about the shortest path algorithms here. See, we have seen BFS. It was for unweighted graph, right? Unweighted. Now let's just talk about the other shortest path algorithms. And now first algorithm is basically shortest path in DAG. What is DAG? DAG is directed acyclic graph. Okay, which means if I have something like this, okay, if I have something like this, then let's suppose this is directed acyclic graph, then I can rewrite this. I'm just redrawing. Okay, I can redraw this particular graph. See, I'm not doing anything. I'm just redrawing. Redraw means it is just helping you to know that it is a directed acyclic graph. Okay, which means what I'm trying to show here is that this given graph, okay, this given graph is basically a directed acyclic graph, but you might not see it easily, so that's why I'm just redrawing it. Okay, this is a redraw of the same graph. Okay, these two are the same graph. Now you notice here that all edges are going from left to right. Okay, all edges are going from left to right. Okay, no edge is going from right to left. So is cycle here? Do you have the cycle here? There is no cycle, right? There is no cycle. So that's why it is called directed acyclic. Okay, A means acyclic. Okay, so this is called directed acyclic graph. Now in this graph, I want to find out the shortest path from S to every other node. Okay, shortest path from S to every other node. Can we do it? Let's just see. Okay, let's just see. So here I want to find out the shortest path from S to every other node, right? Cool. Now suppose you have this particular graph. See, you can apply the complex algorithms which are Dijkstra, Bellman-Ford and these things, but we have very simple idea here. See, what I will do, there is something called as relax and edge. Relax and edge means you just compute the edge weight here, which means initially all edge weights, or maybe you can say all the distances are infinity except this S. Okay, this is, let's suppose, 0. Now you relax all outgoing edges from S. These are the two outgoing edges from S, which means now you will do 0 plus 1, it will be 1, right? Minimum will be 1 at this point in time. Then you would do 0 plus 2, then minimum will be 2 at this point in time. Okay, so this is done. Now you relax all the outgoing edges from C. See, first you relax all the outgoing edges from S, then you relax all the outgoing edges from C. Okay, so all the outgoing edges, which means this is 3. So it will be 3 plus 1. So now it is 4. This is 3 plus 1. Sorry, this is 3 plus 1. This is also 3 plus 1. This will be now 5. So now it will be, sorry, this is 3 plus 1, which is 4. This is also 1 plus 3, which is 4. But this is already 2, right? This is already 2. Since this is already 2, that's why I will not modify that from 2 to 4. Okay. So Govind is asking how you can redraw, how you are redrawing. Just like that. Just see, this is S, you put it S here. This is to A, okay, A and C are there. I mean, it is just a visualization, okay? Just like a visualization. There is nothing I have done here, okay? No algorithm or nothing I have done here. Just like I'm visualizing it like this, okay? I'm just redrawing it. Okay, you will get to understand more, don't worry. So you relax all the outgoing edges from C. Once it is done, you go to this A. Now you relax all the outgoing edges from A. So this is 6 plus 2, it will be 8, right? Now you relax all the outgoing edges from this B, okay? So which is basically 8 plus 1, this is 9. This is 8 plus 1, again this is 9. Will you update from 4 to 9? No, right? So you will not update. Now you relax all the outgoing edges from this. So this is 4 plus 2, which is 6, right? You will update this. So basically, you relax all the outgoing edges from S, then you relax all the outgoing edges from C, then you relax all the outgoing edges from A, then you relax all the outgoing edges from B, then you relax all the outgoing edges from F, then you relax all the outgoing edges from B. So if you do this, then these are the shortest path actually. Okay, these are the shortest path. Okay, these are the shortest path. See, how to draw it, it is, don't worry about it. I mean, they will not ask you to draw. Okay, I will tell you that that you need to find out the something called as topological sort. Okay, so you need to find out topological sort, then you put in that order and then you can draw that. Okay, S2 like this. Okay, you can find out the topological sort, put in that order and then you can draw. This is one way, right? So by the way, you have understood this or not? What is the meaning of relaxing edge? Yeah, this is a good question. Okay, so what is this relax on edge? Relax an edge. What is this meaning? It is just saying that use that edge and see if distance get updated. You just basically go to that edge, which means you go to this edge, right? For example, let me just tell you again. For example, see here that you go to this edge and you relax it. Relax just mean that you update the update may or may not happen. I'm not saying that relax will always need to update. I'm not saying this. What I'm saying, you just consider this edge. Considering the edge is just called relax. Okay, you consider this edge, then this will be 2. You consider this edge or relax this edge, this will be 1. Okay, then you have this vertex, relax all the outgoing edges. Relax means just consider. Okay, you consider this edge, this will be 1 plus 3, this will be 4, this will be 1 plus 3, this is 4, but it is already 2. Okay, it is already 2. So you don't need to update here, right? Now you pick this A, you consider all the outgoing edges. This is 6 plus 2, 8. You pick this B, consider all the outgoing edges. This is 8 plus 1, 9, which is already 4, so not update. 8 plus 1, 9, you will update it. You take this F, consider all the outgoing edges. 4 plus 2, 6, right? So that's all. Okay. Considering the edges is basically called relaxing the edges. Okay, that's all. Considering the edges is basically called relaxing the edges. Okay. Now I have the shortest path from S to everyone. Okay, from S to everyone. If you don't believe me, let's just quickly check. From S to E, is this 6? Is this really 6? Let's just check. Okay, from S to E, is this really 6? Can you tell me? I think this is really 6, right? 1 plus 3, 4, and plus 2, 6. Can you go in lesser than 6? I don't think, because 2 plus 6 is 8. So you can't go in lesser than 6, right? Okay. So basically, from S to this E is 6, and similarly from S to F, if you check in the original graph, then S to F is 4, and so on, right? So this algorithm works, but only for directed acyclic graph. So what is the algorithm? What is the algorithm? Can you tell me? The algorithm is basically start from the leftmost vertex and then keep on relaxing the edges, right? Okay. So basically it work on the negative edges, positive edges, doesn't matter. So basically, let's suppose this is what you have, and then you want to apply the directed acyclic graph shortest algorithm. Okay, then you can say, okay, relax the edge, and so on, right? So you can do this. Now if you want, I can basically, if you want, I can do it for this particular graph also. Okay, just for the sake of practice, let's just do this for this particular graph. So here what they are saying, you keep it 0, you keep everyone else's infinity. Okay, this is infinity, this is, let's suppose, infinity, this is infinity, this is infinity, this is infinity. Now this will be 5. Okay, this will be 3 to start with. Now R is done. Now pick S and relax all the outgoing edges, right? Relax all the outgoing edges. This is 6 plus 5, 11. This is 6 plus 5, 11. This is 5 plus 2, 7, right? This is, but it is already 3, so don't worry about it. So all the outgoing edges is done. Now relax all the outgoing edges from T, right? This is 3 plus 7, 10. This is 3 plus 4, 7. This is 3 plus 2, which is 5. All the outgoing edges from X also. This is 10 plus 1, 11. So don't need to update it. Okay, so see, relax doesn't mean you always update. Relax means you just consider it. Okay, so this is 10 minus 1, 9. Okay, this is, you don't need to update. Okay, this is now 7 minus 2. This is 5. It is already 5, so you don't need to update. So these are the shortest paths we have, right? Understood? Now how much time you will take? How much time you will take here? See, you have to have this topological sort that you can do using DFS. Okay, DFS can find the topological sort in B plus E. Let's suppose you already have the topological sort, or you can find using DFS, which means the order of consideration that you will pick this R or something, right? So how much time you will take here? That is my question. Let's suppose I'm maintaining all these distances in some let's suppose array. Okay, you don't need to consider any heap or something. You can maintain the distances. Initially it is 0, and for everyone else it is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. For everyone else, this is infinity, right? Now you can keep on updating in an unsorted array. Okay, I mean, you don't need to take even the sorted array or something. So unsorted array you can take, right? So how much time this relax will take? Just modifying the value, right? Order of 1. So here the relax operation will take order of 1, because what you are doing is just updating the array entry, right? Here the relax operation is just order of 1, because we are using the unsorted array and it is just update array entry, right? So basically you are just traversing. I think this will just take e time, right? For every edge you will just take order of 1. For every edge order of 1, and finally you have the answer. So e time you will take, just e time. And also there is a hidden time complexity, which is topological sort. Topological sort means, we have already talked in the DFS. Okay, so you can find out the topological sort here of this particular graph, which will take how much time? Using DFS you can take, which is b plus e time. So what is the total time complexity of this algorithm? It also work on the negative edges. So the total time complexity or order of b plus e. Right? You can't use BFS directly because it is weighted. Okay, BFS can't work because it is weighted. Okay, because it is weighted. So we need to find out the topological sort in the order of topological sort. See, this is given, you find out the topological sort. Let's suppose the topological sort you found out, this is the topological sort, right? In the order of topological sort, you pick the vertices and then you keep on relaxing all outgoing edges. Then you pick this, you keep on relaxing all outgoing edges, and then finally you have the shortest path. So what are the steps here? The steps here are just 2 steps. What are the steps? First, find out the topological sort, right? And then relax all the outgoing edges. So find and relax. Relax is just order of 1 here, right? Interestingly, it is just update array entry. Okay. Relax outgoing edges. So this is take order of v plus e. This will just take order of e. So finally order of v plus e is the answer. Now you might be wondering that why this particular algorithm is even working, right? I mean, what is this and why this is even working? And for many of the aspirants, you might not even have seen this, right? This kind of algorithm. So let me just tell you, this is very standard algorithm that I have taken from Corman. Okay, so Corman already have this algorithm, which is DAG shortest path. For the directed acyclic graph, there is a nice algorithm we can do, right? I mean, we can apply Dijkstra. There is something called Dijkstra. We can apply it, right? Nobody stop us to apply this Dijkstra. But what I'm trying to say here is that if we apply Dijkstra, then it will be costly. Okay, it will be costly. Can you apply DFS here? Tell me, can you apply BFS here? In this weighted graph, can you apply BFS? No, you can't apply BFS, but using DFS you can get topological sort, and then you can basically apply the relaxation in that order, right? Which is very light. Okay, order of v plus e only. Dijkstra you can apply, but it is costly. Okay, it is costly. Anyway, now what I'm trying to say here is that why this algorithm even work, right? Why this algorithm is even working? Let me just tell you. See here. See, let me know. There are many people here. Okay, there are many people here who are live. Let me know you are enjoying the session or not. Okay, or you are understanding something from this session or not. Let me know. I will not waste your time. I value your time. So let me know you are enjoying the session or not. Right. So see here, why this particular algorithm is working. See, this R2S. If you are saying that you are relaxing all the outgoing edges, right? And then let's suppose you are at X. Okay, let's suppose you are at X. Now before coming to this X, haven't you explored all the incoming edges to X? Because you have already explored all the outgoing edges from all the vertices, right? So all the incoming edges to X you have explored. Now before coming to X, you are saying that I'm finalizing the path from the shortest path from R to X. I'm already finalizing the shortest path from R to X, right? So which means, see, if I want to know the shortest path from R to X, okay, can it be using any edge that is basically outgoing from X or outgoing from Y or outgoing from Z? Can I be having the shortest path something like this? I mean, can there be edge something like this? First of all, no, right? So if we want to find out the shortest path between R to X, then it must be using all the edges before X, isn't it? Because all the edges after X is not even, can't even reach X, right? So it must be using all the edges before X. Let me know. Must be using all the edges before X, isn't it? So if you have already explored all the edges before X, aren't you getting the shortest path from R to X directly? See, the moment I come to X, I have shortest path to X, right? Path from R to X. Okay. Why? Because from R to everyone I'm exploring, and then I'm saying, okay, from this to everyone I'm exploring. So basically if you are exploring in this order, then you are calculating the shortest path right away. Right? So this is a light in the sense, light algorithm in the sense that it only works for DAG. Okay? Only works for DAG. Let's suppose it is not DAG. Okay? Which means let's suppose it is possible that you have some edge which is something like this. Okay? Let's suppose you have some edge which is also like this. Okay? Also like this. Can you say the moment you come to this X, can you say the shortest path is final? May not be, right? Maybe this edge is minus 500. Maybe something like this, right? I mean you haven't even explored this, or maybe later on you got to know, oh, there is a shortest path. So basically, if it is not a DAG, then you don't know. You can't apply this. Okay, it only works for the DAG. Understood? So there's a nice algorithm which is just order of V plus E. Nice algorithm we have, and only works for DAG. Okay, for DAG. Now the algorithm is shortest path in DAG is looking like something like this. Okay, if you want, you can go through this algorithm later on. Okay, you don't need to go through currently, but yeah, I'm just showing you that you can go through to this algorithm later on. So let me probably go through. I mean, this is very easy. So what is this D? D is just array. Okay, array, unsorted array. See here we are just using unsorted array. We don't need to use heap. We don't need to use priority queue or these fancy things, right? Just unsorted array very nicely. See, this is, you can say this is the crux, or this is the main advantage of this algorithm, that you don't need to use heap. If you have to use heap, then relax operation in the heap, I will tell you in the Dijkstra. Here the relax operation is only taking order of 1. Relax is just considering the edge. In the Dijkstra, I will tell you the relax operation will take log V. Okay, if you're having heap. If you're having heap, then it will be very costly, just like Dijkstra. But here I'm just maintaining the unsorted array. Initially, source 0, everyone infinity. You find out the topological sort, it will take order of V plus E. Okay. For each vertex taken in the topological sort, do this. So you will relax all the outgoing edges, right? So relax operation here is just order of 1. Okay. So for every edge, if you are doing, this loop is running E times. This is just relax is just order of 1. Okay. This is just a printf. This is just like a printf. Okay. This is just like a printf, order of 1. So E into order of 1. So which is just E. So this whole thing is just in E time. Okay. Just E time. Understood? So that's how you can find out the shortest path in the DAG. Okay, let me ask you a question here. A given weighted, not unweighted, a given weighted find shortest path. Okay, then what is most efficient time complexity? Suppose options are order of E square, order of V plus E, order of V plus E into log B or something, and let's suppose the last option is order of you can say something E log E or something, right? So which is the correct answer? order of v plus c, right? This is the most efficient, okay? In case of DAG, right? So the given algorithm that I told you, does this work on the negative edges? The algorithm that we have just seen, does this work on negative edges? Tell me. Yes, the answer is yes. So basically it works on negative, positive, everything, okay? But only on DAG, okay? But only on DAG, right? Now let's say a generalized approach, okay, for the Dijkstra algorithm. I mean, let's say a generalized approach which works for the any weighted graph. Okay, whether it is directed or undirected, but it will only work for the positive edges. I will tell you why. Okay, let's just understand the idea of Dijkstra algorithm. Okay, let's just understand idea. Suppose you are at S. Okay, suppose you have some graph, okay, maybe directed, maybe undirected, let's not worry about it. Okay, Dijkstra works on all kind of graphs, let's not worry about it. Let's suppose you have some graph which is, let's suppose these are the edge weights. Okay, there is, the graph is more, okay, the graph is more. Currently I'm not talking about the whole graph, the graph is more. Let's suppose I'm just exposing you just a partial graph. Okay, I mean there could be many other edges and so on, right? There could be many things. Okay, now you just tell me, suppose if you want to go from, let's suppose you want to go from S to B. Okay, let's suppose you want to go from S to B. In that case, can you tell me what is the shortest path? Can you say that S to B is shortest by looking at just this? Okay, shortest is 2, which means I'm not telling you the whole graph, I'm just telling you the partial graph, and using this partial graph, can you say the shortest from S to B is 2? Tell me. See, I hope my question is clear. What I'm trying to say, that I'm not giving you the whole graph, I'm just giving you the partial graph, right? The partial graph I'm giving you, and then I'm just asking you that S to B is definitely the shortest 2, or maybe there is some other path using A. Is this possible? Yes, this is possible, right? Maybe in future if I tell you that, okay, the complete, this is the complete graph and this was 0.5, this path is, let's suppose, 0.5 or something, right? Then maybe in future you come to know this is actually shortest is 1.5, right? Not 1.5. Is this possible or not? Tell me, let me know. So this is definitely possible that S to B is just 1.5, right? S to B is just 1.5. Definitely possible, right? So what I'm trying to say here is that given this only unexposed, okay, sorry, unexposed partial graph, can you guarantee me what is the shortest path from S to B? Then answer is no. I cannot tell. Using the partial graph, how I can tell, right? No. We don't know the path, shortest path from S to B, right? We don't know the shortest path from S to B. So currently we don't know, obviously. How we can tell using this partial graph only? Is this understood to everyone or not? Because in future, if I tell you the whole graph and if I say that, oh, see, this was 0.5, then you will say that, oh, the shortest is actually 1.5. Isn't it? So just using this partial, can I tell? Then answer is no. Okay, S to B I cannot tell. Understood? Let me know. But let's just extend this idea. Can you tell me just using this partial graph, S to C, what is the shortest? Can you tell me S to C shortest is maybe 3? Can you say S to B shortest maybe 3? S to C? No, right? Maybe in future from A, maybe it is 0.9, okay, maybe 1.9 in future. If I tell you the whole graph, maybe in future you will say, okay, if I tell you the whole graph from this B, it could be just 0.1 and maybe just 2.1 only, right? So you don't know, right? From S to C, can you tell me the shortest? Shortest we can't tell, right? Shortest we don't know yet. Don't know. Okay. Now let me ask you the final question, which is basically S to A. You just tell me from S to A, can you 100% claim the shortest is 1 only? Tell me, from S to A, can you 100% claim the shortest is 1? Can you 100% claim from S to A? See, from S to B we were not able to claim. Similarly, from S to C we were not able to claim. The reason is very simple, because this is not the complete graph. Maybe in future from B I can come in lesser, right? So from S to B also we are not able to claim, because maybe via A I can come here. But just tell me, from S to A can you 100% claim? Just let me know. Then the answer is yes. Here we can claim. Yes, we can claim. Why that is the case? Can you think about it? Why that is the case? See, here the reason is that why I can say about S to A is because in future, even if you come using B, then at least you will carry 2, right? At least you will carry 2, isn't it? At least you will carry 2. In future, if you are coming from B, see, in future if you are coming from C, at least you will carry 3. So what I'm trying to say here is that in future, if you even expose the complete graph, then also that S2, let's suppose you say S2B, then you're at least carrying 2 plus something, right? 2 plus epsilon. So it will be 2 plus epsilon, right? I mean, or 3 plus epsilon, or maybe like, I mean, you will be carrying at least 2, at least 3 like this, right? So if I just tell you only this partial graph, okay? If I just tell you only this partial graph, and then I ask you that from S to A, can you guarantee shortest? Can you guarantee the shortest is 1? Yes. From S to B, can you guarantee shortest is 1? Shortest is 2 or something? So I cannot guarantee shortest here. Can you guarantee S to C? Then I cannot guarantee shortest from here also, right? So I cannot guarantee S to A. I can guarantee from S to A, but I cannot guarantee S to B. I cannot guarantee S to C. So that's what I can claim using this particular partial graph. Yeah, even if this is 0.5, then also the total will be at least 3, right? 3.5. The shortest will still be 1, okay? The shortest will still be 1, isn't it? Let me know. The shortest will still be 1, right? Okay. Given that, here the catch here is that this we can guarantee, given that in future I don't tell, okay, from here to here it was -4. Given that there is no negative edge, okay, given that there is no negative edge, then I can guarantee. So basically, the idea of Dijkstra is coming from the thing that we are assuming there is no negative edge. Okay, so in future I am saying there is no -4, there is no -5, there is no -100, there is no minus. Okay, in future there is no negative edge. So the Dijkstra assumes, so you can say this Dijkstra algorithm, right? So this Dijkstra algorithm assume that there is no negative edges. Otherwise the proof will be not making any sense. So the very first assumption, okay, the very first assumption that we are making is that no negative edge. Otherwise the whole algorithm will not make any sense. Let me know. Okay, this I will clear. This is a major misconception of many students. They think that okay, it can work on the negative edge, but it cannot work on the negative cycle or something. Okay, I will clear this. This is a major misconception of many students. But there is no negative edge. Okay, this is the very first assumption that we need to make. Okay, so I hope now you understood that how the Dijkstra is working, right? So Dijkstra says that given this, let's assume that we don't know the whole graph, but given this, I can say I know the shortest path from S to A, right? I definitely know the shortest path from S to A. Now, if I know the shortest path from S to A, then let me just mark it. Okay, mark means this is the final. Okay, final. The distance is 1 basically, right? Okay, this is the final, which was 0. Okay, initially it is 0. Now the final distance is here 1. Now suppose I explore this. Okay, I explore this particular graph little bit more, and I tell you that okay, these are the, let's suppose I explore this and I tell you the neighbors of these also. Okay, the neighbors of these also. So let's suppose this could be, let's suppose 0.5, this is 3, okay, maybe 2159 or something, right? So see, this was final, so let's not worry about it. Now from S to whatever vertex name it is, let's suppose this is D, okay, this is E, this is F, and like this, right? Okay, so from this will be 1 plus 0.5, this will be 1.5, so this will be 1.5, this is 4, this is 4, this is 3, this is 8, this is 12, and this is already 3. I mean non-final, I'm just having the non-final, right? Okay, and this is 2. Now among all this is 2, this is 3, among all the non-finals 8, 12, 3, 4, 4, 1.5, which one is minimum? Among all non-finals, which one is minimum? See, you need to take minimum between this 1.5, okay, minimum of 1.5, 4, 4, this 2, 3, 2, 3, 3, 8, 12. So which one is minimum? I think this 1.5 is minimum, right? So now I have told you more, okay, I have told you more about the graph. Now you tell me, can you say this is definitely the minimum? I mean, this is definitely the shortest? Or in future, if I tell you more, okay, if I tell you more in future, then will the shortest be changing? Just think about it. In future, if I tell you more about this, okay, more about these edges, then will the shortest be changing? Just tell me. See, in future, if I tell you, if I even explore this, then at least 4 it will carry, at least 4 this will carry, at least 3 this will carry, at least 8 this will carry, at least 12 this will carry, and so on, right? So can it be lesser than 1.5? No, right? It cannot be lesser than 1.5. So basically in future, even if I explore, okay, this whatever I do in future, whatever I do, it cannot be lesser than 1.5. So now I can say from S to A, definitely the minimum is 1.5 only, right? I mean, this is whatever I have written is basically the minimum one. So you can say that this is the shortest, right? This is short. Let's suppose this is the D. So S to D also, you know, is 1.5, right? Let me know if you have understood. So we have taken the minimum among all non-finals, right? All non-finals, whatever is the non-finals here. Now here, interestingly, if you take the minimum between this 2 and whatever this weight is, 2 or whatever, this 2 and 4, then obviously this 4 can never win, right? This 2, this 3 can never win this 2, this 8 can never win this 3, this 12 can never win this 3, which means what I'm trying to say, that if you're taking the minimum, is this really necessary to explore these B and C? Because these will never win, right? If you're taking the minimum, then will this ever win? Among this B and C, will this ever win? No, right? So basically there is no need to explore these also. So that's what Dijkstra says. Dijkstra says that, see, Dijkstra is very, very simple, very nice algorithm. Okay, so it says, see here, from A you can go to, I mean from S to it is final. It says that whatever is the final, you explore that only. Okay, don't explore non-finals. There is no point in exploring because it will never win, right? This will never win. So I mean, sorry, this whatever you are exploring, this will never win. This will never win if you are taking the minimum. So Dijkstra is even more smarter. It says that S2 is final, which is 1. Now in the next iteration, it could happen, okay, it could happen, it is 5, it is 10, it could happen that these are the things, right? In the next iteration, just explore this. Now you tell me the minimum. What is the minimum currently? This is 5, this is 10, this is 2, this is 3. What is the minimum? Minimum is 2, right? So in the next iteration, this could also be the final. See, earlier in the next iteration, these two are contiguously final, right? Which is okay. But this is also okay in the next iteration. This is also the final, right? This is also okay. Dijkstra says that you have the final, you explore the final only, okay, which is called relaxing the edges. Relax the edges from the final vertices, right? I mean, whatever just got final. Okay, is this understood? Basically, let me just tell you, this intuition is nowhere. Okay, I mean, you cannot find this intuition at least in the gate coachings. Okay, In no gate coaching, you will find the proof of Dijkstra. They will just ask you to buy heart. Okay, they will say, okay, just buy heart it. Tell me, in any coaching, have you seen this kind of idea of Dijkstra, that why Dijkstra is working? Tell me this. Have you ever seen that why Dijkstra is working? Is because you can never reach in lesser than 1 from B. And once you get the final, let's suppose this is the case, then this is 1.5, then this must be the final, because you can never reach lesser than 1.5, even if you explore whatever you explore this, right? So you take the minimum and then you will say this is the final thing, right? And Dijkstra does little more smart. It says that don't explore these also. Okay, don't explore these also, right? Dijkstra says that don't explore these also. So it says that you explore, if this is final, you explore only this, which is 5 and 10 maybe, and then this is 2 and 3, then this is the final, right? Okay, now you explore this, and then you keep on doing it. So this is the idea of Dijkstra. Now let me basically work this Dijkstra on one of the graph, right? So let's suppose this is the graph that is of IISc, okay, Indian Institute of Science. This is U block, is one of the hostel there. Anyway, this is mess, this is our department, this is one of the place, Nias Gate, Prakriti, library, and these things, right? So let's run the Dijkstra and let's see how it is working. Okay, how it is working. Let's run Dijkstra and let's see how it is working. So maybe I can directly jump to working let's just directly jump to this particular question. Okay, which is GATE 2004 question. Okay, so let's just see how it is working. Now you are, let's suppose initially you are starting at P. This is 0. Everyone else is infinity. Okay, everyone else you will say infinity. Now from this 0, you will say, okay, from 0 to 1. So this is minimum. I mean, from 0 to 1, you will update that to 1, right? And then you will relax all the outgoing edges from 0. So you will update this to 6. You will update this to 7, right? Let me know if that is okay. So this is 1, 6, 7. You will update all the outgoing edges. Now you take the minimum. What is the minimum among? So this is final. Okay, this is final. So P is final. Now what is the minimum among Q, S, and T, or maybe R and U? What is the minimum? Which means is 1, 6, and 7, and infinity. What is the minimum? I think 1 is minimum, right? So you say that this is final now. And now you explore all the outgoing edges from this Q only. Okay, you explore all the outgoing edges from this Q. Whatever is the minimum, okay, make it final, and you explore all the outgoing edges from that. So this was 1. So this is 1 plus 1, 2. This is 1 plus 4, 5, right? Okay. Now what is minimum among all this 2, 5, 7, and infinity? What is minimum? I think 2 is minimum. So you pick this R, you explore all outgoing edges. So this is 2 plus 2, it is 4, right? This is 2 plus 1, this is 3. Now among this 3, 7, and 4, which is minimum? I think this 3 is minimum. You pick this U, explore all the outgoing edges. There is no outgoing edge, don't worry about it, right? Now this is final. What is non-final? This is S and T are non-final. You pick one of them, which is minimum. S, you pick S, and you explore all the outgoing edges. This is 4 plus 3, 7, right? So this is 4 plus 2, 6. Actually, this is already final, so you don't need to relax this. Okay, you don't need to relax. So this edge has not got relaxed. Okay, I mean, basically, since it is going to already final vertex, so that's why this edge has not got a chance to relax. That is fine. I mean, you may get a chance to relax, or you may not get. I mean, an edge, if it is going to already final, it may not get a chance to relax. Okay, that is fine. So basically, P, Q, R, U, S, and T. This is the answer, right? So P, Q, R, U, S, and T. P, Q, R, U, S, and T. So they are saying in what order? In what order you will relax, right? In what order you will relax? Can you tell me? So this is the order, right? P, Q, R, U, S, and T. Okay. Okay. So what is happening? You pick a first vertex which is 0 and infinity. Everything else is infinity. Then you relax all of its outgoing edges, right? Then you pick next minimum. You relax all the outgoing edges. Can you tell me any edge? Okay, any edge, this edge, or whatever, right? Any outgoing edge, you are relaxing how many times? any edge you are relaxing how many times? Okay, any edge get relaxed how many times? See, you're relaxing this only one time. Whenever you pick P, then only you're relaxing this, right? So every edge is relaxing only one time. This is only one time, right? This only one time, this only one time. But there is some edge, maybe this two, 0 time, because it is going to already final, right? So you can say at most one time. Why? Because whenever you are picking this, then only you're relaxing outgoing edges, right? Or this particular edge will be relaxed only when you are picking Q, and you are picking Q only once, right? You will not pick it twice. If it is minimum, you will pick it. So you will pick it only once, and then only you will relax it. And see, picking is done. Now relaxing will depend whether it is going to the final vertex or it is going to the non-final vertex, right? So basically what I'm trying to say here is that if you're picking this, then you may relax it or may not relax it. So at most one time. This edge will not get relaxed 2 times, or any edge will not get relaxed 2 times. At most one time. Why? Because whenever you're picking this, then only you're relaxing outgoing edge. Now this outgoing edge will get relaxed only at at most one time. Why? Because whenever you're picking it, then only you're relaxing it, and you may relax at that time or may not relax, depending that this edge is going to the final vertex or not, right? Okay. Now relaxing means that this is, let's suppose 5, this is 9. If this is 2, then you will make it 7. But if it is 6, then you will not update it, right? 5 plus 2 is 7, so you will not update it. So relaxing may update or may not update, right? This is update, this is may not update. So relax is very simple, just like DAG, okay? Just like DAG. So it is nothing special here, right? In the previous algorithm, it like same thing. In the previous algorithm, this was unsorted array, if you remember. Okay, unsorted array in DAG. Do you remember this? And hence, relax was order of 1. Okay, but here we need to take min heap. I will tell you why. Okay, min heap in Dijkstra. Okay, that's why relax is costly. Okay, here relax is costly. Okay, we will see why. Okay, we will see why. So let's just quickly run Dijkstra on this particular graph, and let's just see how it is working. So this is initially 0, everything else is infinity, right? Everything else is infinity. Now what you will do, you will say, okay, this is 3, this is, you will relax all the outgoing edges, right? Now what is the minimum among 3, 1, infinity, infinity, infinity? I think 1 is minimum, so this is done. This one you will say it is done. Now you relax this is 5, but you don't need to update it. This is also 5, you can update it, right? Now what is the minimum among 3, 5, infinity, infinity? I think 3 is minimum. You pick this will be 5. Okay, so this is 5, this is 4, right? Okay, so what is the minimum among this 4, 5, infinity? I think 4 is minimum. You pick this outgoing edge or relax all the outgoing edges, 4 plus 1, 5. So you will update it. Now what is the minimum among these two? I think anything. So you can pick anything. Let's suppose you pick this 3. So you will say that, okay, you relax all the outgoing edges. This is already, see, this edge will never get relaxed, right? This edge will never get relaxed. Why? The reason is that if you pick this 3, this is going to the final vertex, right? So this edge will not get relaxed. Then this edge will get relaxed. Yeah, this edge will get relaxed, but it will not get updated. Okay, it will get relaxed, but it will not get updated. So 5 plus 2 is 7, but it is 5. So anyway, so these are the final answers, right? So 0, 3, 1, 5, 5, and 4. Okay. Okay. Now let's just see if Dijkstra works on the negative edges or not. Suppose I have maybe I have one example here. Okay, let's suppose I have this example. Okay, this is 4, 6, this is -3, this is 2. First of all, tell me, does this graph has negative edge? Does this graph has negative edge? First of all, tell me. The answer is yes, because this is the negative edge. Does this graph have negative cycle? Tell me. Does this graph has negative cycle also? Just see here. Is this even having any cycle? Negative, positive is okay, but it is even having any cycle? Okay, let me just remove this. So what about negative edge? And what about the negative cycle? So negative cycle, obviously no, right? It doesn't have negative cycle. Then the answer is no, right? Okay, there is no cycle, neither negative nor positive. Okay, there is no cycle. Okay, anyway, so this here, if you apply the Dijkstra, it will say it is 0, it is infinity. Okay, and everyone else is infinity. Now you relax this, it will be 4. You relax this, it will be 2, right? Now you pick minimum among 2, 4 and infinity. Which is minimum? I think 2 is minimum. You will pick this. Then you relax all the outgoing edges from 2. There is no outgoing edge, so that's fine. You pick this 4. Then 4 plus 6 is 10, right? Okay. Okay. Now can you tell me? What are the minimum? What are the shortest path from 0 to 1? So this is 4. This is 4 as per the Dijkstra. This is 10 as per the Dijkstra, and this is basically 2 as per the Dijkstra, right? Is this correct? Are these paths correct? Even though there is a negative edge, so there is a negative edge. Is this giving you correct answer? Tell me. This is 4. This is 6. So this is 10, and then this is direct, which is 2. Yes. So the answer is correct, right? So here, in this particular example, okay, let me just remove this for now. So in this particular example that I have just given you, Dijkstra works, right? Dijkstra works. Is there negative cycle? No. There is a negative edge. Just there is a negative edge, and Dijkstra is working. Okay. Okay. Let's just see more. Okay. Let's just see more. Okay. See, there is no cycle. It is not a cycle. Okay. There is no 4, 6, and then this is still 3 only. This is not going like this. This edge is not like this. There is no cycle. Now you tell me, in this particular graph, can you tell me is Dijkstra working? If I basically make, instead of -3, if I just make -9, is Dijkstra working here? Let's just quickly check. This is 0, this is infinity, this is infinity, this is infinity. Then this will be relaxed. This is 4, this will be relaxed to 2, right? Now you pick the minimum, you pick the 2 edge minimum, right? There is no edge. Okay, now you pick the next minimum. This is 4 plus 6, 10. So Dijkstra is now saying this is 0 is minimum, 4 is minimum, 2 is minimum, and 10 is minimum. Is Dijkstra giving you the correct answer? Tell me. Does Dijkstra give you the correct answer here? See, here, in this case, from 0 to 3, I think you can go in 1, right? You can go in 1. But Dijkstra is telling you 2. You can go in 1. Okay, 1 is shortest. But Dijkstra is telling you 2. See, in this particular example, Dijkstra is working. But in this particular example, Dijkstra is not working. Right? So earlier Dijkstra is working, and now Dijkstra is not working. Just because I have modified this -3 to -9. So what do you think? What is the reason that see here in one of the graph? Okay, so these are the 2 examples that we have, I think, taken. Okay, not these 2. So these are the 2 examples we have taken. In one of the graph, in one of the example, Dijkstra is working, and another example, Dijkstra is not working. No, Dijkstra doesn't relax this edge. See, this is very important to understand. Dijkstra doesn't relax. Why? Because this is already final, right? This is already final. And even though, see, there are many examples. I don't have. Even though if you relax the final edges also, then also there are many examples that Dijkstra won't work. Okay, I will tell you why. See, Dijkstra is not made for negative edges. Let me just tell you what is the reason. Let's suppose Let's have a very simple example here. Okay. Let's suppose that I apply the Dijkstra. Dijkstra will say that S to B is what? Dijkstra will say S to B is how much? S to B is 1, right? So this is 0 initially, this is infinity, this is infinity. Dijkstra will say that okay, this is 5, you relax all the outgoing edges, this is 5, and then this is 1. So Dijkstra will say okay, this is now final because among this 5 and 1, this 1 is minimum, this is final, right? And now you relax all the outgoing, there is no outgoing edge, now you will say this 5 is final. So Dijkstra will give you 1 and 5. Is this correct? Tell me. No, right? Because the shortest from here to here is basically minus 95 or something. This one is not correct, but Dijkstra is giving you 1. So what went wrong, right? So what went wrong here? Can you tell me? See, the reason is that the basic algorithm Dijkstra is working like this. I'm saying Dijkstra is a greedy algorithm basically. I'm saying that if I'm going to S to B, if this is 1 and this is 5, okay, from S, if I'm saying this B, this is A, I have explored this S. If I'm saying this is 5 and sorry, this is 1 and this is 5, let's suppose I'm saying something like this, then I'm basically saying that okay, S to B is 1 is minimum. According to Dijkstra, S to B 1 is minimum. Why? Because I'm claiming here that in future, see, here I'm claiming that in future there won't be any. See, I'm claiming that S to B is final. Why? Because in future there won't be any path from A to B which will be negative. See, I'm saying that at least cost 5 will be there. If you want to go via A, then I'm saying that at least cost 5 is there. But that is not being obeyed, right? So basically it is not being followed. It is not being followed. Why? Because here I'm having negative. Right? Here I'm having negative. So this S2, if you apply the Dijkstra, S2B is final. S2 is final. And then why? Because this is among 5 and 1, this is minimum. So what is the minimum? Dijkstra will take it, right? Whatever is the minimum, Dijkstra will take it. It will say it is final. Why I'm able to say it is final? Because I'm saying that okay, in future it won't be the case that you won't get surprised. Okay, there is no surprise for future. Okay, there is no surprise in future. You won't say that there will be some negative edge, right? This is the basic assumption of Dijkstra. So that is why Dijkstra is failing. So the thing here is that Dijkstra, see, Dijkstra is working here but failing here, right? Failing in this example. So the thing here is that Dijkstra is not even made for the negative edges, right? So you can say Dijkstra or Dijkstra, whatever you want to pronounce, Dijkstra is not even made for negative edges. Right? This is the basic assumption in Dijkstra that in future there is no surprise. See, this kind of explanation, again I'm telling you, you will not find in any gate coaching at least, right? Tell me any good gate coaching which have given you the clear explanation that why Dijkstra work, okay, the intuitive proof of Dijkstra, okay, why Dijkstra is working like this, right? So these are the intuitive proofs that I've told you, right? Idea of this Dijkstra, right? These kind of explanation will not be told you. So I will just request you that once this session is over, just comment it out on the YouTube, okay? Just comment it out and let us know if you have liked this session. This will definitely motivate us. Okay, so if Dijkstra work on some negative edge graph, then what is the reason? Can you tell me the reason? For example, it is working on this negative edge graph, right? The Dijkstra is working. What is the reason? Can you tell me the reason? The reason is, if Dijkstra is working on any negative graph, then what is the reason? Reason is, it is just luck. Okay, no reason actually. Dijkstra is not even made for the negative edges. Okay, it is just a luck. It is just a luck that it is working. right? There is no Dijkstra is not made for the negative edges. You need to understand that. Understood? It is just by luck. Okay. So do Dijkstra work on the negative edges? So Dijkstra does not, I mean, may or may not work, you can say. If it is working, it is just by luck. Okay. So I will, okay, let me not write it again. So if it is working, it is just by luck. Understood? If Dijkstra is working for the negative edges, it is just by luck. This is very important to understand. Okay. Now I hope you understood that about the Dijkstra. Now let's just solve few questions. I think we have many questions here. Okay, and then we will see the Bellman-Ford, and see, I will tell you that why Bellman-Ford work. Okay, just like Dijkstra, I will also tell you why this is most interesting. Okay, most interesting proof. Very nice idea that why Bellman-Ford work. I will tell you. Okay, don't worry. So for now, let's just solve few questions here. Consider the following strategy: solve the single source shortest path with a positive integer weight. Okay, there is no negative. Now they are saying replace each edge weight W by W of weight 1 unconnected intermittent. Okay, so okay, I will tell you about these things. Let me first solve few other questions, right? Okay, so let's solve this Stanford question. So what they're saying, the shortest path from the source node to every other node, right, will remain unchanged if the positive constant value is added. So they are saying, let's suppose there is a shortest path. Okay, there is a shortest path from S to let's suppose T. If you add, let's suppose, if you in this graph, let's suppose if you add, okay, there, I mean, this is the graph. Let's suppose in this graph, if you add something, let's suppose you add 5. Okay, every edge weight you add 5. Then they are saying that the shortest path will not change. Is this true? Is this true? See, see, I think if you have seen the AIMT solution, I think there I have told you that this is not true. Why? Because suppose that earlier shortest path, see, it might be the case that earlier shortest path is just containing, maybe it is containing three edges of 1 1 1, right? And let's suppose this is the graph, and let's suppose this is 4. Okay, now you add plus 5 everywhere. Okay, you add plus 5 everywhere. This is plus 5, this is plus 5, this is plus 5, this is plus 5. See, before adding plus 5, can you tell me what is the shortest from S to T? Before adding plus 5, what is the shortest? The shortest is the upper one, right? This is shortest. So if you add plus 5, then what is going to be the shortest? This will be 6 into 3. This is 18, and this will be 9, right? This will be 9 only. So the shortest is now this. So basically, if you add plus 5 or anything, right, then the shortest may change, right? This is the shortest which is getting changed, right? So now you can say shortest may change. Understood? Now shortest may change. What is the reason? Because earlier the shortest path may be having, let's suppose three edges. Now if you're adding plus 5, it is not uniform, which means you are adding 15 somewhere, you're adding 5 somewhere. It is not uniform, right? Since it is not uniform, that is why you are adding 15 in one path, you are adding 5 in one path. That is why the shortest path may change. 15 in this path, 5 in this path. And similarly, let's suppose if I say, if I just give you this, okay, to start with, let's suppose I give you this. If I say you subtract, okay, you add, or maybe I give you this. This is the shortest, right? This is the shortest. Let's suppose if I subtract, okay, minus 5 everywhere, then you will get this. If you do minus 5 everywhere, you will get this. Then earlier the shortest path is this. Now the shortest path got changed, isn't it? Why that is the case? Because this is having just 1, so you are subtracting just 5 here. but you are subtracting more here, right? You are subtracting more here. So this becomes shortest. So here, if you're adding or you're subtracting, in both the cases, the shortest path may change. Let me know if that is fine to everyone, right? Let me know. Okay. So basically, what is the core reason behind it? The core reason is that earlier, okay, earlier you were, let's suppose you were comparing, okay, let's suppose that earlier you were comparing between let's suppose this is only one node or maybe multiple nodes. Let's suppose you are comparing, this is x, y, z, and this is, let's suppose, pq. Okay. So you were saying that, okay, x plus y plus z is basically lesser than p plus q. I mean, that's why this x plus y plus z was shortest, right? Okay. So earlier, this is earlier, but now whenever you are adding or subtracting, it actually doesn't matter, right? So now it might so happen, let's suppose you're adding, right? So how much you will add here? How much you will add here? Let's suppose you're adding w everywhere. So you will add 3w, because you are adding w here, you are adding w here, you are adding w here, right? You are adding w here, you are adding w here. So it will be 2w, right? So you don't know. It will depend on the value of w and so on, right? So basically you don't know. Now you don't know whether this is lesser or this is greater, right? Maybe, see, earlier this was greater. P plus q was greater. Now maybe just because you are adding extra w here. So effectively you are adding one extra w here. Maybe it is this p plus q is still greater. Isn't it? Maybe this p plus q is still greater. Maybe because of this extra w, it may have got greater. So you don't know. Basically, you are not uniformly adding. Understood? You are not uniformly adding. So you don't know the relationship, right? Here you don't know, right? Don't know greater or lesser. Understood? So that is why whether you add or you subtract, you never know. But let's suppose you are dividing. Okay, let's suppose you are dividing or you are multiplying or something, right? Let's suppose you are multiplying. If you are multiplying, then what's going to happen? Let's just see. Okay, if you are multiplying, then what's going to happen? Let's just see. Suppose you are multiplying with w. Okay, then it will become, this is x plus y plus z. Okay, this will become wx plus wy plus wz. This will become p plus wq. So this will be w of p plus q, and similarly this will be w of p plus q, right? X plus y plus z. Now w will get cancelled out. If you are multiplying, can't you definitely say that still the relationship hold? If you are multiplying, then can't you definitely say that still the relationship hold? See, if you are adding, then you don't know, because you are non-uniformly adding, right? You're not adding uniformly. So if you're adding, then you don't know. But if you are multiplying, then you know. So multiplication, because it will get eventually it will eventually get cancelled out. So for the multiplication, you know. So you can say a positive constant is added, then it will not change, remain unchanged. It may change, right? May change for the positive constant. Okay, if you multiply, then this is the answer, right? A positive constant is subtracted. Subtracted may change. Multiply or divide, it will be the answer, right? So what is the answer here? The answer is B and D, right? The answer is B and D. Let's just see the answer. Yeah, B and D. This is, by the way, the Stanford question, right? This is a Stanford question. Let me know if you have understood this completely. This is a Stanford question. You can see direct question at this link. Understood, right? Okay, great. So I hope you understood, right? You understood the idea behind Dijkstra. Now we have seen the examples, right? We have seen examples of Dijkstra. We have seen BFS details. We have seen DAG shortest path algorithm also. So we have seen many things, right? And this particular idea, let me tell you, it took me a long to understand, okay, that why Dijkstra is working. So it may seem very easy to you that if I'm explaining, but it took too long for me to understand that why Dijkstra is working. So I will just request you to comment out here that if you have understood this idea completely, okay, immediately after this live streaming end. So you just comment out that if you have understood that idea completely. And in the next session, we will see many other questions, okay, from the standard universities like MIT, Stanford, and then we will see Belmont also. So we will see Belmont, we will see many other questions, okay, in the next session. Okay. In case of multiply, you are multiplying with everyone, right? So now you are comparing W into X plus Y plus Z, and you are comparing W into P plus Q. So essentially you are comparing just this, right? If earlier this relationship hold, now also this relationship hold, right? That's what I'm saying. Now also this relationship hold, right? If earlier this hold, then also now also this holds. Okay. Okay. So everyone, if you have loved this session, just let us know. Okay. Just comment it out if you have really loved this session. If you understood everything, we will bring more sessions. We will bring more sessions on OS. We will bring more sessions on CN and many other subjects, right? So just comment it out and let us know. Okay. And in the next session, I will first finish. Okay. Tomorrow I will finish this Bellman-Ford and other things, right? Bellman-Ford and all the gate PYQs. Okay. All gate PYQs. So I think today it is little late. Already we are quite late. So that's why in tomorrow's session I will cover all the gate PYQs, Bellman-Ford and everything, right? Okay. So basically, I hope you specifically liked this BFS layers, right? This BFS layers, that how the BFS is working using the layers, right? This BFS layers and these things. And this is actually very nice idea. I hope you understood this completely, right? And we have solved many gate PYQs using the BFS layers, such as this. See, these kind of PYQs we were able to solve very easily, right? Okay. So thank you everyone. Take care. Bye bye. Let's meet tomorrow. Okay. Take care.